Time dilation, a concept that feels as though it were pulled from the pages of a dream, is in fact one of the most fundamental and experimentally verified truths about the universe we inhabit. It is a whisper from the fabric of reality itself, a secret told by Einstein's theories of relativity, that time is not the rigid, unyielding metronome we perceive in our daily lives. It is not a universal clock, ticking at the same rate for everyone, everywhere. Instead, time is a fluid, malleable, and personal experience, a river whose current can speed up or slow down depending on how fast you move through space or how deeply you are immersed in the well of gravity. Imagine a spaceship, a vessel of human curiosity, embarking on a journey to the stars at a speed that is a significant fraction of the speed of light. For the astronauts on board, the clocks on the wall would tick normally, their hearts would beat at a familiar rhythm, and their thoughts would unfold in a seemingly ordinary sequence. They would feel no different. But for those of us left behind on Earth, a strange and beautiful magic would be at play. We would see their clocks ticking more slowly, their movements unfolding in a subtle slow motion, their entire existence stretched out over a longer period of our time. This is not an illusion, not a trick of perception. It is a physical reality. The astronauts are, in a very real sense, traveling into our future. They could complete a journey that, to them, lasts only a few years, only to return to an Earth where decades, or even centuries, have passed. Their friends, their families, their entire world would be a memory, a ghost from a distant past. This is the profound and unsettling promise of time dilation. And its influence is not just confined to the hypothetical realm of near-light-speed travel. It is a phenomenon that is woven into the very structure of the cosmos. According to Einstein's general theory of relativity, time is also affected by gravity. The stronger the gravitational field, the slower the flow of time. An observer standing on the surface of a massive star would age more slowly than an observer floating in the empty space between the galaxies. And at the ultimate gravitational extreme, at the event horizon of a black hole, time, from the perspective of a distant observer, would seem to grind to a complete halt. A clock falling into a black hole would appear to tick slower and slower, its final tick stretching out for an eternity, forever frozen at the point of no return. These are not just theoretical curiosities. They are essential features of our universe, phenomena that have practical implications for our technologies, like the GPS satellites that orbit our planet, and profound implications for our understanding of the nature of reality itself. Time dilation is a gateway to some of the deepest questions we can ask about the universe, about the relationship between space and time, about the nature of aging, and about the very meaning of a human life in the vast and wonderfully strange expanse of the cosmos. The concept of time dilation, this strange and beautiful elasticity of time, is a direct and unavoidable consequence of one of the most profound and elegant principles in all of science, the constancy of the speed of light. In the late 19th century, physicists were grappling with a deep puzzle. James Clerk Maxwell's brilliant theory of electromagnetism predicted that light is an electromagnetic wave that travels at a specific, fixed speed, approximately 300,000 kilometers per second. But a speed must be measured relative to something. The speed of a car is measured relative to the road. The speed of a sound wave is measured relative to the air it travels through. So, what was the speed of light measured relative to? The prevailing theory was that of the luminiferous ether, a hypothetical, invisible, and all-pervading substance that filled all of space and acted as the medium for light waves. But a series of brilliant and increasingly precise experiments, most famously the Michelson-Morley experiment of 1887, failed to detect any evidence of this ether. The speed of light seemed to be the same, no matter how fast the observer was moving relative to the hypothetical ether. It was a deep and troubling paradox. And it was a young, unknown patent clerk in Bern, Switzerland, named Albert Einstein, who, in his miracle year of 1905, had the courage and the genius to resolve it. He took the seemingly paradoxical experimental result as a fundamental postulate. The speed of light in a vacuum, he declared, is the same for all observers in uniform motion, regardless of the motion of the light source. This simple, elegant, and radical idea is the cornerstone of his special theory of relativity. And from this single postulate, all the strange and wonderful consequences of relativity, including time dilation, flow with an inexorable mathematical logic. Imagine a simple light clock on a spaceship. It consists of two mirrors, one on the ceiling and one on the floor, with a single photon of light bouncing between them. Each time the photon hits a mirror, the clock ticks. For an observer on the spaceship, the photon travels a simple vertical path up and down, and the clock ticks at a regular rate. Now, imagine this spaceship is flying past a stationary observer on Earth at a very high speed. From the Earth-bound observer's perspective, the photon is not traveling a simple vertical path. Because the spaceship is moving, the photon must travel along a diagonal path to get from one mirror to the other. And here is the crucial point. According to Einstein's postulate, the speed of light is the same for both observers. Since the Earth-bound observer sees the photon traveling a longer distance, but at the same speed, it must, by simple logic, take a longer amount of time for that photon to complete its journey. This means that, from the perspective of the observer on Earth, the light clock on the spaceship is ticking more slowly. And since the laws of physics must be the same for all observers, this slowing down cannot just apply to the light clock. It must apply to all physical processes on the spaceship, including the chemical reactions in the astronauts' bodies and the electrical signals in their brains. Time itself, for the moving observer, is running slow. This is not a matter of perception. It is a matter of the fundamental geometry of space-time. Einstein's great insight was that space and time are not separate, independent entities. As Newton had believed, they are two aspects of a single, unified, four-dimensional continuum, space-time. And the geometry of this space-time is such that the speed of light is the ultimate, cosmic speed limit. As an object accelerates and moves faster through the three dimensions of space, it must, by necessity, move slower through the one dimension of time. This is the deep and beautiful truth that lies at the heart of time dilation. It is a truth that has been confirmed by countless experiments, from the observation of decaying subatomic particles to the precise measurements of atomic clocks. And it is a truth that forever shattered our classical, intuitive, and comforting notion of a single, universal, and absolute time. The theory of relativity, in its two magnificent forms, special and general, is the single greatest intellectual achievement of the 20th century. And it is the product of the singular genius of one man, Albert Einstein. The journey began in 1905 with his special theory of relativity, a theory that dealt with the laws of physics for observers in uniform, non-accelerating motion. As we have seen, this theory was built on two simple but revolutionary postulates that the laws of physics are the same for all inertial observers and that the speed of light in a vacuum is a universal constant. From these two starting points, Einstein was able to derive a host of strange and counterintuitive, but experimentally verified consequences. He showed that time is relative, that a moving clock ticks more slowly than a stationary one. He showed that space is relative, that a moving object appears to contract in its direction of motion, a phenomenon known as length contraction. He showed that mass and energy are two sides of the same coin, related by the most famous equation in all of science, E equals mc squared. And he showed that the concept of simultaneity is relative. Two events that appear to happen at the same time for one observer may not appear to be simultaneous for another observer who is in motion relative to the first. These were ideas that completely upended the classical Newtonian worldview, which was based on the concepts of absolute space, absolute time, and absolute simultaneity. But special relativity, as its name implies, was a special case. It did not include the effects of acceleration or of gravity, and for the next decade, Einstein grappled with the challenge of incorporating gravity into his new relativistic framework. The result, published in 1915, was his general theory of relativity, a theory of gravity that is, by any measure, a masterpiece of human thought. The central insight of general relativity is the principle of equivalence, the idea that the effects of gravity are indistinguishable from the effects of acceleration. An observer in a sealed, windowless room cannot tell the difference between being at rest in a gravitational field, like on the surface of the Earth, and being in a rocket that is accelerating at a constant rate in deep space. From this simple, powerful insight, Einstein was led to a radical new conception of gravity. Gravity is not a force that acts at a distance between two massive objects, as Newton had believed. Gravity is the curvature of spacetime, mass and energy. He proposed, tell spacetime how to curve, and the curvature of spacetime tells mass and energy how to move. A massive object, like the sun, creates a dent or a warp in the fabric of spacetime around it. And a smaller object, like a planet, is not being pulled by the sun. It is simply following the straightest possible path, a geodesic, through this curved space-time. It is like a marble rolling on a stretched rubber sheet that has been deformed by a heavy bowling ball at its center. The general theory of relativity also made a number of new and dramatic predictions, including the phenomenon of gravitational time dilation. The theory predicts that time runs slower in a stronger gravitational field. A clock at sea level will tick slightly slower than a clock on top of a mountain. This is not just a theoretical curiosity. It is a real, measurable effect that must be accounted for in the operation of our GPS satellites, which rely on incredibly precise timing to determine our location. The theory also predicted that the path of light should be bent by gravity. This was famously confirmed in 1919 during a solar eclipse, when the British astronomer Sir Arthur Eddington observed that the apparent position of the stars near the edge of the sun was shifted, their light having been bent as it passed through the sun's powerful gravitational field. This observation made Einstein an overnight global celebrity and cemented the place of general relativity as our new and improved theory of gravity. Einstein's theories have had a profound and lasting impact on almost every area of modern physics, from cosmology and astrophysics to particle physics and quantum mechanics. They have given us a new and beautiful language for describing the universe, a language that has allowed us to understand the birth of the cosmos in the Big Bang, the strange and violent lives of black holes, and the subtle, relativistic effects that are a part of our everyday technological world. The phenomenon of time dilation, as predicted by Einstein's special theory of relativity, is a direct and logical consequence of the universe's most fundamental and perplexing law, the constancy of the speed of light. To truly understand why a moving clock runs slow, we must abandon our intuitive, everyday notions of time and space and embrace the strange, but beautiful geometry of a four-dimensional spacetime. Imagine, once again, our two twins, let's call them Stella, the astronaut who embarks on a high-speed journey to a distant star, and Terra, her brother who remains on Earth. Stella's spaceship is a marvel of future technology, capable of accelerating to a speed that is a significant fraction of the speed of light. As she travels, from her own perspective, time flows normally. She eats her meals, she conducts her experiments, she sleeps and dreams, and her onboard clock ticks at a steady, familiar rate. But from Terra's perspective on Earth, a strange and wonderful transformation is taking place. As Stella's spaceship accelerates, Terra would observe that everything on board, including Stella's clock, begins to run more slowly. The closer Stella gets to the speed of light, the more pronounced this effect becomes. This is not because of any mechanical problem with the clock, it is because time itself, in Stella's moving frame of reference, is flowing at a different rate than time in Terra's stationary frame. The mathematical relationship that governs this effect is the Lorentz factor, often denoted by the Greek letter gamma. The Lorentz factor depends on the relative velocity between the two observers, and it is a measure of how much time is stretched or dilated for the moving observer for everyday speeds. The Lorentz factor is so close to 1 that the effect of time dilation is completely negligible. But as the velocity approaches the speed of light, the Lorentz factor begins to increase dramatically, approaching infinity as the velocity approaches the speed of light itself. This means that for an object traveling at the speed of light, like a photon, time does not pass at all. From a photon's point of view, it is emitted and absorbed at the same instant, and the entire journey across the universe takes no time. The constancy of the speed of light for all observers is the key that unlocks this mystery. Because the speed of light is the same for both Stella and Terra, but the distance that light must travel in certain thought experiments is different for each of them. Then time itself must be the variable that changes to keep the speed of light constant. The implications of this are profound. It means that there is no universal now. The concept of simultaneity is relative. Two events that are simultaneous for Terra on Earth may not be simultaneous for Stella on her high-speed spaceship. Her slice of the present moment in the four-dimensional block universe is tilted relative to Terra's. This has been confirmed by a host of experiments. The most famous of these is the observation of decaying muons. Muons are unstable, subatomic particles that are created in the Earth's upper atmosphere when cosmic rays strike air molecules. They have a very short half-life of about 2.2 microseconds. If time were absolute, even a muon traveling at nearly the speed of light would not have enough time to travel from the upper atmosphere to the surface of the Earth before it decayed. But we detect a large number of muons at sea level. The reason is time dilation. From our perspective on Earth, the muon's internal clock is running incredibly slowly, which allows it to survive for much longer than its normal half-life and to complete the journey to the ground. From the muon's perspective, its own lifetime is normal, but the distance from the upper atmosphere to the ground is length contracted due to its high speed, making the journey a much shorter one. Both perspectives give the same correct answer. A beautiful demonstration of the self-consistency of relativity. Time dilation is not a paradox. It is a fundamental and beautiful feature of a universe where the speed of light is the supreme and unchanging law, the mathematical heart of special relativity. The engine that drives the strange and wonderful phenomena of time dilation and length contraction is a set of equations known as the Lorentz transformations. These transformations are the rules that tell us how to translate the measurements of space and time made by one observer into the measurements made by another observer who is in motion relative to the first. And at the core of these transformations lies the Lorentz factor, a simple but powerful mathematical expression that captures the very essence of relativistic effects. The Lorentz factor, typically represented by the Greek letter gamma, is defined as 1 divided by the square root of 1 minus the ratio of the square of the relative velocity to the square of the speed of light. This might seem like an intimidating formula, but its behavior is actually quite simple and intuitive. When the relative velocity is 0, the Lorentz factor is exactly 1. This is our familiar, everyday, non-relativistic world, where time and space appear to be absolute, As the velocity increases, the Lorentz factor also increases, but very, very slowly at first. For the speeds of our everyday experience, a car on the highway, a jet airplane, the Lorentz factor is so infinitesimally close to 1 that the relativistic effects are completely unmeasurable. But as the velocity begins to approach the speed of light, the Lorentz factor starts to grow much more rapidly. At 87% of the speed of light, the Lorentz factor is 2. This means that a moving clock would appear to run at half the speed of a stationary clock, and a moving object would appear to be contracted to half its length. At 99.5% of the speed of light, the Lorentz factor is 10, and as the velocity gets ever closer to the speed of light, the Lorentz factor approaches infinity. This has a number of profound physical consequences. The formula for time dilation is simple. The time interval measured by a stationary observer is equal to the time interval measured by the moving observer multiplied by the Lorentz factor. Since gamma is always greater than or equal to 1, this means that the stationary observer always measures a longer time interval. The moving clock always runs slow. The formula for length contraction is the inverse. The length measured by the stationary observer is equal to the length measured by the moving observer divided by the Lorentz factor. This means that the moving object always appears to be shorter in its direction of motion. The Lorentz factor also appears in the formula for relativistic mass. An object's mass is not a constant, but increases with its velocity. The relativistic mass is equal to the rest mass multiplied by the Lorentz factor. As an object approaches the speed of light, its mass approaches infinity. This is the reason why nothing with mass can ever reach the speed of light. It would require an infinite amount of energy to accelerate an infinite mass. The speed of light is the ultimate, cosmic speed limit. The Lorentz factor is not just a mathematical curiosity. It is a physical reality that has been confirmed by countless experiments. The time dilation of decaying muons, the relativistic effects in our GPS satellites, the energy required to accelerate particles in our great particle colliders like the Large Hadron Collider. All of these are described with perfect accuracy by the Lorentz transformations and the Lorentz factor. The story of the Lorentz factor is a beautiful example of the power of mathematical physics. It is a story of how a simple, elegant mathematical expression derived from a set of profound physical principles can unlock a whole new and deeper understanding of the fundamental nature of space, of time, and of reality itself. The speed of light, approximately 300,000 kilometers per second, is not just a very fast speed. It is the ultimate cosmic speed limit, a fundamental and unbreakable law of the universe. This is one of the most profound and far-reaching consequences of Einstein's theory of relativity. But why is this so? The answer lies in the deep and intimate relationship between mass, energy, and the geometry of space-time. As we have seen, as an object with mass is accelerated, its relativistic mass increases, multiplied by the Lorentz factor. As its velocity gets closer and closer to the speed of light, its mass approaches infinity. To accelerate an object with infinite mass would require an infinite amount of energy, which is a physical impossibility. And so, the speed of light acts as an insurmountable barrier, a finish line that massive objects can approach, but never quite reach. This has profound implications for our understanding of time. As an object moves faster through space, it necessarily moves slower through time. The speed of light is the ultimate trade-off. A massless particle, like a photon, travels at the speed of light, and for it, time does not pass at all. From a photon's point of view, its journey across the universe, from a distant star to your eye, is an instantaneous one. For an object at rest, time passes at its maximum rate. And for everything in between, there is a sliding scale, a continuous trade-off between motion in space and motion in time, all governed by the requirement that the total speed through the four-dimensional continuum of space-time is always equal to the speed of light. The speed of light is not just a speed limit. It is the very constant that holds the fabric of space-time together, the conversion factor between space and time. This has practical implications for our technology. The GPS system, which we rely on for navigation in our cars, on our phones, and in our airplanes, is a beautiful and everyday demonstration of the reality of these relativistic effects. The GPS satellites orbit the Earth at a speed of about 14,000 kilometers per hour. This is a very fast speed, but it is still a tiny fraction of the speed of light. And yet, the effects of relativity are not negligible. There are two relativistic effects that must be accounted for. The first is special relativity, or time dilation due to velocity. Because the satellites are moving so fast, their onboard atomic clocks run slightly slower than the clocks on the ground, by about 7 microseconds per day. The second is general relativity, or time dilation due to gravity. Because the satellites are in a much weaker gravitational field than we are on the surface of the Earth, their clocks run slightly faster than ours, by about 45 microseconds per day. The net effect is that the satellite clocks run faster than the ground clocks by about 38 microseconds per day. This may not sound like much, but the GPS system relies on timing signals with a precision of just a few nanoseconds. If these relativistic corrections were not made, the GPS system would accumulate a positioning error of about 10 kilometers every single day. Within a week, it would be completely useless. The fact that your phone can tell you your location with an accuracy of just a few meters is a direct, daily, and powerful confirmation of the reality of Einstein's strange and beautiful theories of relativity. It is a testament to the fact that the universe operates on a set of rules that are often counterintuitive, but that are also precise, predictable, and deeply woven into the fabric of our technological world. The phenomenon of time dilation is a direct consequence of the relative velocity between two observers. The faster the relative speed, the more pronounced the effect. This leads to some truly mind-bending, and yet physically real scenarios when we consider the comparison between observers moving at different high velocities. Imagine three observers: Terra, who is at rest on Earth; Stella, who is in a spaceship traveling at 80% of the speed of light relative to Earth; and Luna, who is in another spaceship traveling in the same direction at 99% of the speed of light. From Terra's perspective, both Stella's clock and Luna's clock will be running slow. And because Luna is moving faster, her clock will be running significantly slower than Stella's. Now, what does the situation look like from Stella's perspective? She will see Terra's clock on the receding Earth as running slow. This is a direct consequence of the principle of relativity. From Stella's point of view, it is the Earth that is moving, and so its clock must be time dilated. She will also see Luna's clock, which is moving away from her at a high, but sublight, speed, as running slow. The key here is that the time dilation effect always depends on the relative velocity between the two frames of reference being compared. There is no absolute and correct rate of time. Each observer's experience of time is equally valid within their own frame of reference. This is the source of the famous twin paradox. The paradox arises from a seeming contradiction. If motion is relative, then the twin who stays on Earth sees the traveling twin's clock as running slow. But the traveling twin sees the Earth twin's clock as running slow. So, when they are reunited, who is actually younger? The resolution to this paradox lies in the fact that the two twins' experiences are not symmetrical. The traveling twin must accelerate to leave the Earth, turn around at their destination, and then decelerate to return. The Earth twin remains in a single, inertial frame of reference for the entire journey. It is this acceleration that breaks the symmetry and makes the traveling twin's experience of time fundamentally different. A full analysis using general relativity, which can handle accelerating frames, shows that it is indeed the traveling twin who will be younger upon their return. The twin paradox is not a true paradox. It is a beautiful and profound illustration of the deep and subtle nature of time in a relativistic universe. The effect of time dilation is not just a theoretical curiosity. It has been measured with incredible precision in a variety of different contexts. The time dilation of fast-moving muons is one such example. Another is the behavior of atomic clocks. In the famous Haffel-Keating experiment of 1971, several cesium atomic clocks were flown around the world on commercial airliners, once eastward and once westward, when their times were compared with a reference clock that had remained on the ground. The traveling clocks were found to have lost or gained a few nanoseconds, in perfect agreement with the predictions of both special and general relativity. These are incredibly small effects, but they are real. And they are a powerful confirmation of the fact that the rate at which time passes is not a universal constant, but is a function of one's motion and one's position in a gravitational field. The twin paradox is perhaps the most famous and most misunderstood of all the consequences of special relativity. It is a thought experiment that, on the surface, seems to reveal a deep and fatal contradiction in Einstein's theory, but which, on a deeper analysis, reveals the profound and beautiful consistency of the relativistic worldview. The setup is simple. We have a pair of identical twins. One, let's call him the Earth twin, remains at home on Earth. The other, the space twin, embarks on a long, high-speed journey to a distant star and back. According to special relativity, from the Earth twin's perspective, the space twin is moving at a high velocity, and so his clock and his entire biological aging process should be running slow. So, when the space twin returns, he should be younger than the Earth twin. So far, so good. But here is the paradox. According to the principle of relativity, all uniform motion is relative. From the space twin's perspective, it is the Earth that is moving away from him at a high speed, and so he should see the Earth twin's clock as running slow. So, when he returns, he should expect the Earth twin to be younger than him. This is the apparent contradiction. Both twins cannot be younger than the other. So, who is right? The resolution lies in a subtle but crucial detail that is often overlooked. The two twins' journeys are not symmetrical. The Earth twin remains in a single, inertial frame of reference for the entire duration of the experiment. The space twin, on the other hand, must undergo a series of accelerations. He must accelerate to leave the Earth. He must decelerate to stop at the distant star. He must accelerate again to begin his journey home. And he must decelerate one final time to land back on Earth. It is this acceleration that breaks the symmetry between the two twins and makes their experiences of time fundamentally different. Special relativity, in its original form, only deals with inertial frames. To fully analyze the situation of the space twin, we need to use the more powerful framework of Einstein's general theory of relativity, which can handle accelerating frames of reference. In general relativity, acceleration is equivalent to a gravitational field. When the space twin is accelerating, it is as if he is in a strong gravitational field, and according to general relativity, clocks run slower in a stronger gravitational field. So, during his periods of acceleration, the space twin will see the Earth twin's clock as running faster than his own. A detailed calculation shows that this effect of the clock speeding up during the acceleration phases more than compensates for the effect of the clock slowing down during the constant velocity phases of the journey. The net result is that, upon his return, the space twin will find that the Earth twin has indeed aged more than him. There is no paradox. The theory is perfectly self-consistent. The twin paradox is a powerful illustration of the fact that in a relativistic universe, there is no single, objective flow of time. The amount of time that elapses between two events, like the space twin's departure and his return, is not an absolute quantity. It depends on the path that is taken through spacetime between those two events. The Earth twin takes a straight path through spacetime, a path of no acceleration. The space twin takes a curved path through spacetime, a path that involves acceleration. And just as the shortest distance between 2 points in space is a straight line, the longest proper time between two events in spacetime is the straight, inertial path. By accelerating, the space twin has taken a shortcut through time, and so he has experienced less of it. The distinction between gravitational time dilation and time dilation due to high speeds is a crucial one, as it reflects the distinction between Einstein's two great theories of relativity. While both phenomena involve the stretching or slowing of time, they arise from fundamentally different physical principles. Time dilation due to high speeds, or relativistic time dilation, is a consequence of special relativity. As we have seen, it arises from the fundamental postulate that the speed of light is the same for all observers in uniform motion. It is a purely kinematic effect, a consequence of the geometry of a flat, four-dimensional spacetime. It depends only on the relative velocity between two observers. The faster you move relative to me, the slower your clock will appear to be ticking from my perspective. And, symmetrically, the slower my clock will appear to be ticking from your perspective. This effect is independent of any forces or masses. It is a feature of the very fabric of space and time. Gravitational time dilation, on the other hand, is a consequence of general relativity. It is a dynamic effect, a consequence of the curvature of spacetime by the presence of mass and energy. It does not depend on the relative velocity of two observers, but on their relative position in a gravitational field. The deeper you are in a gravitational well, the stronger the gravity, the more curved the spacetime, and the slower the flow of time. A clock at the bottom of a mountain will tick more slowly than a clock at the top, not because of its speed, but because it is in a slightly stronger gravitational field. This effect has been confirmed with incredible precision by experiments like the Pound-Rebka experiment, which measured the tiny gravitational redshift of photons as they traveled up a tower at Harvard University. These two effects, the kinematic effect of special relativity and the gravitational effect of general relativity, are not mutually exclusive. They can, and often do, occur at the same time. The GPS satellites are a perfect example. They are in orbit around the Earth, which means they are in a weaker gravitational field than we are on the surface. This causes their onboard clocks to run faster than ours, due to gravitational time dilation, but they are also moving at a very high speed relative to us. This causes their clocks to run slower than ours, due to relativistic time dilation. The two effects work in opposite directions, but they are not equal in magnitude. The gravitational effect is larger than the velocity effect. The net result is that the satellite clocks run faster than the ground clocks by about 38 microseconds per day, a difference that must be precisely accounted for to make the GPS system work. The ultimate expression of gravitational time dilation is found near a black hole. At the event horizon of a black hole, the gravitational field is so strong that time, from the perspective of a distant observer, appears to come to a complete stop. An object falling into a black hole would appear to freeze at the horizon, its light redshifted into oblivion, its final moment stretched out for an eternity. For the object itself, however, time would continue to flow normally as it crossed the horizon and plunged into the singularity at the center. This is the ultimate and most terrifying demonstration of the relativity of time. In the end, the two forms of time dilation are two different manifestations of the same, deep, underlying truth that time is not a separate, independent, and absolute entity, but is an integral and dynamic part of the four-dimensional fabric of space-time. A fabric that can be stretched, warped, and curved by the presence of motion and of mass. The Lorentz factor, that simple but powerful mathematical expression that lies at the heart of special relativity, is more than just a formula. It is a bridge, a translator, a key that allows us to move between the different perspectives of different observers in our strange and beautiful relativistic universe. Its significance extends beyond the phenomenon of time dilation. It is the mathematical thread that weaves together all the strange and counterintuitive consequences of Einstein's theory, showing them to be not a collection of independent curiosities, but a single, coherent, and self-consistent whole. We have seen how the Lorentz factor governs time dilation, stretching the time of a moving observer from the perspective of a stationary one, but it also governs the phenomenon of length contraction. As an object approaches the speed of light, not only does its time slow down, but its length, in the direction of motion, appears to contract. The formula for this is the inverse of the time dilation formula. The measured length is the proper length divided by the Lorentz factor as the velocity approaches the speed of light. The Lorentz factor approaches infinity, and the length of the object approaches zero. From the perspective of a stationary observer, a near light-speed spaceship would appear to be flattened into an almost two-dimensional pancake. This, again, is not an illusion. It is a real physical consequence of the geometry of space-time. It is what allows the fast-moving muon to perceive the distance from the upper atmosphere to the Earth's surface as being much shorter than we do, allowing it to complete the journey before it decays. The Lorentz factor is also the key to understanding the relativity of simultaneity. Two events that are simultaneous in one frame of reference are not, in general, simultaneous in another. The Lorentz transformations, which are the full set of equations that relate the space and time coordinates of two different frames, contain the Lorentz factor, and they show precisely how the slice of the present moment is tilted for a moving observer. This is perhaps the most profound and philosophically challenging of all the consequences of relativity. It does away with the very notion of a universal now. And, most famously, the Lorentz factor is at the heart of the relationship between mass and energy. The formula for relativistic mass states that an object's mass increases with its velocity, multiplied by the Lorentz factor. This is why it takes more and more energy to accelerate an object as it gets closer and closer to the speed of light. The energy is not just increasing the object's kinetic energy, it is also being converted into mass. This leads directly to Einstein's most famous equation, E equals mc squared, which is, in a sense, a statement about the energy an object has even when it is at rest. The Lorentz factor is the mathematical glue that holds the relativistic universe together. It ensures that the laws of physics are the same for all observers. It ensures that the speed of light is a universal constant. And it ensures that all the strange and wonderful consequences of relativity, the slowing of time, the shrinking of space, the increase of mass are all interconnected and mutually consistent. It is a beautiful example of the unreasonable effectiveness of mathematics in the natural sciences. As the physicist Eugene Wigner famously put it, it is a testament to the fact that the universe, at its deepest level, seems to be governed by a set of simple, elegant, and powerful mathematical principles. Principles that we, as conscious, questioning beings, are privileged to be able to discover and to understand. The concept of an inertial frame of reference is a cornerstone of physics, a seemingly simple idea that is, in fact, the foundation upon which both Newtonian mechanics and Einstein's special theory of relativity are built. An inertial frame is, in its essence, a perspective, a coordinate system from which the laws of motion take their simplest form. It is a frame of reference that is not accelerating. An observer at rest, or an observer moving at a constant velocity in a straight line, is in an inertial frame. An observer in a car that is speeding up, slowing down, or turning a corner is in a non-inertial frame. In an inertial frame. Newton's first law of motion holds true: an object at rest will stay at rest, and an object in motion will stay in motion with the same speed and in the same direction, unless acted upon by an external force. In a non-inertial frame, this is not the case. If you are in an accelerating car, a ball placed on the dashboard will appear to accelerate backwards, even though no force is acting on it. This is a fictitious force, a consequence of the acceleration of your frame of reference. The principle of relativity, in its original Galilean form, states that the laws of mechanics are the same in all inertial frame. This means that there is no absolute state of rest. You cannot perform any mechanical experiment within a closed, windowless room to determine whether you are at rest or moving at a constant velocity. Einstein, in his special theory of relativity, elevated this principle to a universal law, stating that all the laws of physics, including the laws of electromagnetism, are the same in all inertial frames. And it was this simple, powerful idea, when combined with the experimental fact of the constancy of the speed of light, that led to the revolutionary conclusion that measurements of space and time must be relative. The concept of time dilation is fundamentally a statement about the relationship between two different inertial frames. If an observer in one inertial frame measures the time interval between two events, and an observer in another inertial frame, moving relative to the first, also measures the time interval between the same two events, their measurements will, in general, not agree. The time interval measured by the moving observer will always be longer, by a factor of gamma, the Lorentz factor. This is not a matter of one observer being right and the other being wrong. Both measurements are equally valid within their own frame of reference. There is no privileged absolute frame of reference, no cosmic master clock against which all other clocks can be compared. This has profound implications for our understanding of simultaneity. In Newtonian physics, time is absolute, and so is simultaneity. If two events happen at the same time for one observer, they happen at the same time for all observers. But in a relativistic universe, this is not the case. The concept of now is not universal. Two events that are simultaneous in one inertial frame may happen at different times in another. Imagine a long, high-speed train with a light source at its exact center. If the light source flashes, an observer on the train will see the light reach the front and the back of the train at the same instant. For her, these two events are simultaneous. But for an observer standing on the platform as the train whizzes by, the situation is different. He will see the light traveling towards the back of the train, which is moving towards the light, and towards the front of the train, which is moving away from the light. Since the speed of light is the same in all directions for the platform observer, he will see the light reach the back of the train before it reaches the front. For him, the two events are not simultaneous. The very concept of a universal present moment, a single now that is shared by the entire universe, is a casualty of Einstein's revolution. Each inertial frame has its own unique slice of spacetime that it considers to be the present. The concept of an inertial frame of reference, which began as a simple idealization in the physics of motion, has, through the lens of relativity, become a key that has unlocked a deeper and far more subtle understanding of the very fabric of space, of time, and of reality itself. The reality of time dilation is not just a theoretical prediction. It is a well-established experimental fact. a phenomenon that has been confirmed with incredible precision in a variety of different physical systems. The history of the experimental verification of time dilation is a beautiful story of the interplay between theoretical insight and technological ingenuity, a story of how we have learned to measure the subtle and often fleeting effects of relativity in our own macroscopic world. One of the first, and still most compelling, pieces of evidence comes from the world of particle physics. As we have seen, muons are unstable, subatomic particles with a very short half-life of about 2.2 microseconds, in a classic experiment first performed in the 1940s and repeated with increasing precision ever since. Scientists have measured the flux of muons created in the upper atmosphere as a function of altitude. By comparing the number of muons detected at the top of a mountain with the number detected at sea level, they can determine how many have decayed during their journey through the atmosphere. The results are in perfect agreement with the predictions of special relativity. Far more muons reach the surface than would be expected if time were absolute. A direct and powerful confirmation of the time dilation of these fast-moving particles. The world of atomic clocks has provided another, and even more precise, testing ground for relativity. An atomic clock is an incredibly stable and accurate timekeeping device that uses the resonant frequency of atoms, like cesium, as its pendulum. In the famous Hafele-Keating experiment of 1971, several of these clocks were flown around the world on commercial airliners. When their times were compared with a reference clock at the U.S. Naval Observatory, they were found to have gained or lost a few hundred nanoseconds, in precise agreement with the combined effects of kinematic and gravitational time dilation predicted by relativity. In the decades since, these kinds of experiments have been repeated with ever-increasing accuracy, using more stable clocks, faster aircraft, and even sounding rockets. One of the most beautiful of these was the Gravity Probe, an experiment in 1976, which launched a hydrogen maser clock to an altitude of 10,000 kilometers and compared its ticking rate with a clock on the ground via a microwave link, confirming the predictions of gravitational time dilation to a precision of about 70 parts per million. And, as we have discussed, the entire multi-billion-dollar global positioning system is a continuously running global experiment in relativity. The 38 microsecond per day difference between the satellite clocks and the ground clocks is not a small correction. It is an essential part of the system's design. Without it, the system would fail within minutes. The fact that GPS works, that it can guide us to our destinations with an accuracy of just a few meters, is a daily and powerful testament to the reality of Einstein's theories. In the world of particle accelerators, time dilation is an everyday reality. The unstable particles that are created in high-energy collisions, like pions and kaons, are traveling at speeds incredibly close to the speed of light. Their lifetimes are stretched by a huge Lorentz factor, which allows them to travel for many meters through the detectors before they decay. The design of these massive and complex experiments is completely dependent on a precise, relativistic understanding of the behavior of these particles. The evidence is overwhelming and unambiguous. Time dilation is not a paradox, a fantasy, or a philosophical speculation. It is a real, measurable, and well-understood feature of the physical world. It is a phenomenon that challenges our everyday intuition, but one that is also a beautiful and profound confirmation of the deep, geometric, and wonderfully counterintuitive nature of the space-time we inhabit. The effects of time dilation on the human body, on the subjective experience of aging, are a classic and compelling theme of science fiction. A theme that allows us to explore the profound and often poignant human consequences of Einstein's strange and beautiful theory. In our everyday lives, the relativistic effects are so vanishingly small that they are completely unnoticeable. The astronauts on the International Space Station, for example, are traveling at about 28,000 kilometers per hour, a very fast speed by terrestrial standards, but it is still only about 0.0025% of the speed of light. Over the course of a 6-month mission, they will have aged a few milliseconds less than their counterparts on Earth. It is a real measurable effect, but not one that you would notice in the mirror. But if we could one day build a spacecraft that could travel at a significant fraction of the speed of light, the effects would become dramatic. Imagine a mission to our nearest stellar neighbor, Proxima Centauri, 4.2 light-years away. If a spacecraft could travel at a constant speed of 99% of the speed of light, the journey, from the perspective of an observer on Earth, would take about 4.25 years. But for the astronauts on board, the Lorentz factor would be about 7. This means that they would only experience about 1/7 of that time. Their journey, to them, would last only about 7 months. They would arrive at Proxima Centauri having aged less than a year, while over 4 years had passed on Earth. And if they were to make the round trip, they would return to an Earth that was almost 8.5 years older. While they themselves had aged by less than 2 years, this is the essence of the twin paradox, and it is a real physical possibility. The implications of this for interstellar travel are profound. It means that a journey to the stars, which seems impossibly long on a human timescale, could be completed within the lifetime of the crew. A journey to the center of our galaxy, 26,000 light-years away, could be completed in just a few decades of ship time, if the spacecraft could maintain a constant acceleration of 1 g. But the price of this time travel into the future is a complete and irreversible disconnection from the world that was left behind. The interstellar explorer would become a time traveler, a ghost from the past, returning to a future that is no longer their own. Their friends, their family, their entire civilization would be a memory. This is a theme that has been explored with great poignancy in works of science fiction, from Poul Anderson's novel Tau Zero to the movie Interstellar. It is a theme that touches on some of our deepest human feelings, our connection to our past, our hopes for our future, our love for our families, and our fear of loss and of loneliness. The physical effects of time dilation on the aging process itself are not thought to be significant. The biological processes of our bodies are governed by the laws of physics, and so they would slow down in the same way as any other physical process. The astronauts would not feel any different. But the long-term health effects of the journey itself, the exposure to cosmic radiation, the potential effects of high acceleration, the psychological stress of isolation would be a major concern. The dream of interstellar travel is a dream that is both inspiring and deeply melancholic. It is a dream of reaching for the stars, but it is also a dream that involves a profound and perhaps unbearable sacrifice. It is a reminder that the laws of physics, while beautiful and elegant, can also be a harsh and unforgiving mistress. The practical applications of Einstein's theory of relativity, and of time dilation in particular, are a beautiful and powerful demonstration of the deep and often unexpected connection between fundamental, curiosity-driven research and the technologies that shape our everyday lives. The most famous and most important of these is the Global Positioning System. The GPS is a constellation of about 30 satellites orbiting the Earth at an altitude of about 20,000 kilometers and a speed of about 14,000 kilometers per hour. Each satellite carries an incredibly precise atomic clock, and it is constantly broadcasting a time-stamped signal. Your GPS receiver on the ground picks up the signals from at least 4 of these satellites, and by precisely measuring the time it takes for each signal to arrive, it can calculate its distance to each satellite and, through a process of trilateration, determine its own position on the surface of the Earth with an accuracy of just a few meters. The entire system is a marvel of precision timing, and it would be completely useless without relativity. As we have seen, the clocks on the GPS satellites are subject to two relativistic effects. Because they are moving so fast, their clocks run slower than ours by about 7 microseconds per day. And because they are in a weaker gravitational field, their clocks run faster than ours by about 45 microseconds per day. The net effect is that the satellite clocks gain about 38 microseconds on the ground clocks every single day. This may not sound like much, but light travels about 300 meters in a microsecond. If this relativistic correction were not accounted for, the GPS system would accumulate a positioning error of over 10 kilometers every single day. The system is designed with this in mind. The frequency of the onboard clocks is deliberately set to be slightly slower than their nominal frequency on the ground, so that once they are in orbit, the combined effects of relativity will cause them to tick at the correct rate from our perspective. The GPS is a continuously running, global-scale experiment that confirms the predictions of both special and general relativity with stunning precision, every single second of every single day. Another, more subtle, application of relativity is in the world of particle physics and medical technology. Particle accelerators, like the Large Hadron Collider, which are used to probe the fundamental structure of matter, must be designed using the principles of special relativity. The particles in these machines are accelerated to speeds so close to the speed of light that their relativistic mass is thousands of times greater than their rest mass. The design of the magnets that steer and focus these particles, and the timing of the radio frequency cavities that accelerate them, must all take these relativistic effects into account. A related technology, the medical PET scanner, relies on the production of positrons, the antimatter counterparts of electrons. These positrons are produced by the radioactive decay of isotopes that are created in a small on-site cyclotron, a type of particle accelerator. The design and operation of this cyclotron is another application of the principles of special relativity. Even a technology as seemingly simple as an old-fashioned cathode ray tube television set has a touch of relativity in it. The electrons that are fired at the screen to create the image are accelerated to a significant fraction of the speed of light, about 30%. The design of the magnetic coils that deflect these electrons to scan across the screen must account for their relativistic mass increase. The story of the applications of relativity is a powerful reminder that there is no such thing as useless knowledge. The abstract and seemingly esoteric theories that are born from our pure human curiosity about the fundamental nature of the universe can, in time, become the foundations of the technologies that we rely on in our daily lives, often in ways that we do not even realize. The synchronization of clocks, a seemingly simple and mundane task, becomes a profound and complex issue in a relativistic universe. In our classical Newtonian worldview, time is absolute. There is a single, universal now that is shared by all observers, everywhere. In this picture, synchronizing two clocks is a straightforward matter. You simply set them to the same time, and as long as they are good clocks, they will stay synchronized forever. But in Einstein's universe, time is relative. The rate at which a clock ticks depends on its motion and its position in a gravitational field. And the very concept of simultaneity is relative. Two events that are simultaneous for one observer may not be simultaneous for another. This means that the synchronization of distant clocks is not a trivial matter. It is a process that is deeply intertwined with the fundamental structure of spacetime. The standard procedure for synchronizing two distant stationary clocks in an inertial frame is the Einstein synchronization convention. Imagine you have two clocks, A and B, a known distance apart. You send a light signal from clock A to clock B. The moment the signal is sent, you record the time on clock A. When the signal arrives at clock B, it is immediately reflected back to clock A. When the reflected signal arrives back at clock A, you record the time on clock A again. Clock B is then defined as being synchronized with clock A if the time it recorded for the arrival of the signal is exactly halfway between the departure and return times recorded by clock A. This procedure seems simple and logical, but it has a deep and often unappreciated consequence. It is a convention, a definition. It is based on the assumption that the speed of light is the same in both directions, from A to B and from B to A. While this is a very natural and reasonable assumption, it is not something that can be experimentally verified without already having a set of synchronized clocks. This circularity has led to a long and subtle philosophical debate about the conventionality of simultaneity. But for all practical purposes, the Einstein synchronization convention is the standard by which we define a consistent frame of reference in special relativity. The challenge of synchronization becomes even more acute when we consider clocks that are in motion relative to each other, or that are in different gravitational fields. The clocks on the GPS satellites, for example, must be constantly synchronized with each other and with a network of ground-based master clocks. This is a complex process that involves a constant exchange of timing signals and a sophisticated set of relativistic corrections that account for both the special relativistic effects of their velocity and the general relativistic effects of their altitude. The problem of synchronization is not just a technological one, it is also a fundamental one. It is a problem that forces us to grapple with the deep and often counterintuitive nature of time in a relativistic universe. It is a reminder that time is not a pre-existing, absolute background, but is a dynamic and relational quantity, a quantity that is woven into the very fabric of spacetime, and whose measurement is fundamentally dependent on the state of motion and the gravitational environment of the observer. The relationship between velocity, acceleration, and time dilation is a subtle and often misunderstood aspect of relativity. It is velocity, the relative speed between two inertial frames. That is the direct cause of the kinematic time dilation of special relativity. But it is acceleration that is the key to resolving the apparent paradoxes, like the twin paradox, and to understanding the transition between different inertial frames. According to special relativity, an observer in an inertial frame will see the clock of another observer, who is moving at a constant velocity relative to them, as running slow. This is a symmetrical effect. The second observer will also see the first observer's clock as running slow. This symmetry is broken when one of the observers accelerates. Acceleration is not relative, it is absolute. An observer in a sealed, windowless room can perform an experiment to determine if they are accelerating. They can watch a pendulum, or they can drop a ball. If they are in an inertial frame, the pendulum will hang straight down and the ball will fall to the floor. If they are accelerating, the pendulum will hang at an angle and the ball will fall in a curved path. Because acceleration is absolute, it allows us to distinguish between the experiences of the two twins in the twin paradox. The Earth twin remains in a single inertial frame. The space twin undergoes a series of accelerations, which moves them from one inertial frame to another. The effect of this acceleration on the aging process is not a direct one. The acceleration itself does not cause the time dilation. The amount of time dilation depends only on the velocity during the journey. But the acceleration is what makes the journey possible, and it is what breaks the symmetry between the two twins. There is, however, a more direct connection between acceleration and time in the context of general relativity. The principle of equivalence, the cornerstone of general relativity, states that the effects of a uniform gravitational field are indistinguishable from the effects of a uniform acceleration. This means that an accelerating frame of reference has an effective gravitational field. And just as clocks run slower in a real gravitational field, they also run slower in an accelerating frame. This is a more dynamic and subtle effect than the simple kinematic time dilation of special relativity. Imagine a large, rotating space station designed to create an artificial gravity through its centrifugal force. An observer at the center of the station would be in a non-accelerating frame, while an observer on the rim would be in a constantly accelerating frame. According to general relativity, the clock of the observer on the rim would tick more slowly than the clock of the observer at the center. This is a real physical effect, and it is another manifestation of the deep and intimate connection between the geometry of space-time, the motion of objects, and the flow of time. The interplay between velocity, acceleration, and time is a beautiful and complex dance, a dance that is choreographed by the laws of relativity. It is a dance that is playing out on a grand, cosmic scale in the motions of the planets and the stars. And it is a dance that is also at the heart of our most advanced technologies, like the GPS. And it is a dance that will be central to our future as a spacefaring species, as we learn to build the machines that will carry us at ever-increasing speeds and accelerations out into the vast and beckoning wilderness of the cosmos. The subjective, human experience of time is a rich, complex, and deeply mysterious phenomenon. It is a world of memory, of anticipation, of the fleeting, precious moment of now. And it is a world that can be profoundly altered by our emotional and psychological state. In moments of intense joy or terror, time can seem to slow down, each second stretching out for an eternity. In moments of boredom or routine, time can seem to fly by, hours disappearing in the blink of an eye. This subjective, psychological experience of time is, of course, very different from the objective, physical time that is measured by our clocks and described by the laws of physics. And yet, the discoveries of relativity, with their revelation that physical time is not absolute, but is a fluid and observer-dependent quantity, have created a new and fascinating space for a dialogue between the worlds of physics and of human experience. The idea that time can stretch and contract, that its flow is not a universal constant, is an idea that resonates deeply with our own inner experience. Time dilation, in this sense, is not just a strange quirk of the physical world. It is also a powerful metaphor for the elasticity of our own subjective time. But is it possible that there is a deeper, more than metaphorical connection? Could the profound, and often life-altering, shifts in our perception of time that can occur in altered states of consciousness in deep meditation, in mystical experiences, or in the throes of a profound personal crisis, be a sign that our consciousness is, in some way, capable of detaching from the rigid clock time of our everyday reality and accessing a more fundamental, more timeless level of being? This is a speculative but deeply compelling idea. The philosophical implications of time dilation are profound and far-reaching. The abolition of a universal now, the relativity of simultaneity, is a direct challenge to our common-sense view of the world as a single, unfolding story that is shared by all observers. It suggests a block universe picture of reality, where past, present, and future all exist in a timeless, four-dimensional landscape. And the flow of time is an illusion of our consciousness, a spotlight that moves along our own personal world line. This is a vision of reality that can be both unsettling and deeply comforting. It is unsettling because it seems to do away with the possibility of free will and an open future. If the future is already there, in what sense are our choices real? But it can also be comforting because it suggests a kind of immortality. In the block universe, the past is not gone. It is simply in a different part of the space-time block. The loved ones we have lost, the moments of joy we have experienced are not erased. They are a permanent and indelible part of the four-dimensional tapestry of reality. The twin paradox, with its story of two siblings whose lives unfold at different rates, is a powerful metaphor for the human condition itself. We are all, in a sense, time travelers on our own, unique paths through spacetime. Our choices, our experiences, our relationships, all shape the unique trajectory of our own personal world line, and while we may start at the same point, and we may end at the same point, the amount of time we experience along the way, the richness and the depth of our own lived journey, is our own unique creation. The physics of time dilation is not just a set of abstract equations. It is a new and profound lens through which we can view our own lives, our own relationships, and our own fleeting and precious place in the grand, mysterious, and beautifully relativistic drama of the cosmos. The precise and reliable measurement of time is one of the cornerstones of modern science and technology. And at the heart of this endeavor lies the atomic clock, a device of almost unimaginable accuracy and stability. An atomic clock is not like a conventional clock that relies on the mechanical oscillation of a pendulum or a quartz crystal. It is a quantum device that uses the intrinsic and universally constant frequency of a specific atomic transition as its timekeeping standard. The international definition of the second, for example, is based on the frequency of the radiation that is emitted or absorbed when a cesium-130 atom makes a transition between two very specific, hyperfine energy levels in its ground state. This frequency is, by definition, exactly 9,192,631,770 cycles per second. To build an atomic clock, a sample of cesium atoms is first cooled with lasers to a temperature of just a few millionths of a degree above absolute zero. This slows the atoms down to a crawl, which allows for a much more precise measurement. The cold atoms are then gently tossed upwards, like a slow-motion fountain, through a microwave cavity. Inside the cavity, they are irradiated with a microwave signal that is tuned to be as close as possible to the cesium transition frequency. If the microwave frequency is exactly right, many of the atoms will make the transition to the higher energy state. The atoms are then detected, and a feedback loop is used to adjust the microwave frequency to maximize the number of atoms that make the transition. This locks the microwave oscillator to the natural and universally constant frequency of the cesium atom. The stability of modern atomic clocks is staggering. The best laboratory-based optical lattice clocks, which use atoms like strontium or ytterbium that have a much higher transition frequency in the optical part of the spectrum, are now so stable that they would not lose or gain a single second in over 15 billion years, an amount of time that is longer than the entire age of the universe. This incredible precision is what has allowed physicists to perform some of the most stringent and beautiful tests of Einstein's theory of relativity. By comparing the ticking rates of two of these clocks, it is possible to measure the effects of time dilation with a sensitivity that is almost beyond belief. In a famous experiment in 2010, physicists at the National Institute of Standards and Technology were able to measure the effect of gravitational time dilation over a height difference of just 33 centimeters, about 1 foot. They found that the clock that was higher up did indeed tick slightly faster, by about 90 parts in a quadrillion, in perfect agreement with the prediction of general relativity. The atomic clock is a beautiful and powerful example of the synergy between fundamental science and advanced technology. It is a device that is born from our deep quantum mechanical understanding of the atom. And it is a device that, in turn, allows us to test the very foundations of our theories of space, of time, and of gravity, with an accuracy that would have been unimaginable to Einstein himself. And it is a technology that has a profound, if often invisible, impact on our everyday lives. Through its essential role in the global positioning system and in the synchronization of the global communication networks that are the backbone of our modern, interconnected world. The dream of human space travel to the distant stars is a dream that is, at its heart, a battle against the tyranny of time. The distances are so vast that even at the speed of light, a journey to our nearest stellar neighbors would take years, and a journey across our own galaxy would take 100,000 years. For a human crew, traveling at the much slower speeds that are possible with our current or near-term technology, these journeys would take millennia. But time dilation, the strange and wonderful consequence of special relativity, offers a potential and tantalizing loophole. As a spacecraft approached the speed of light, the flow of time on board, from the perspective of an observer on Earth, slows down. This means that a journey that takes centuries, or even millennia, of Earth time could be completed in just a few decades of ship time. The crew could travel to the stars and back within their own lifetimes. But this solution to the problem of time comes at a profound and poignant price, the price of a complete and irreversible disconnection from the human world that was left behind. The interstellar explorer would become a time traveler, a visitor from the past, returning to a future that is no longer their own. This is the central human drama of interstellar travel. And it is a drama that is further complicated by the challenge of communication. A spacecraft traveling to a star that is 10 light-years away will have a 10-year communication lag with Earth. A message sent from the ship will take 10 years to arrive, and the reply will take another 10 years to return. The crew would be in a state of profound and unprecedented isolation. Their connection to home, a series of faint, delayed whispers across the vast, dark gulf of interstellar space. And this is where time dilation adds another cruel twist. Because the crew is aging more slowly than the people on Earth, the communication lag will be experienced asymmetrically. A child on Earth could send a message to their astronaut parent, and by the time the parent's reply is received, that child could have grown up, lived an entire life, and died of old age, while the parent has aged by only a few years. The emotional and psychological challenges of such a situation are almost impossible to imagine. The crew would be living in a constant state of temporal dissonance, their own and subjective experience of time completely out of sync with the historical time of their home world. They would be ghosts, living in a moving bubble of the past, forever cut off from the present moment of the civilization they left behind. And what of the society that sends them a multi-generational interstellar mission would require a level of long-term commitment, of societal stability, and of shared purpose that is far beyond anything our current, short-sighted, and fractured world has ever been able to achieve? It would require a civilization that is willing to invest its resources in a project whose ultimate payoff will not be seen for centuries. The challenges of interstellar travel are not just technological. They are also deeply human, deeply psychological, and deeply societal. They force us to confront our own mortal limitations, our own deep need for connection, and the very nature of our relationship with time itself. And yet, the dream persists. It is a dream that is driven by one of the most powerful and noble of all human impulses, the desire to explore, to know, to see what lies beyond the next horizon. And perhaps one day, if we can become a wise enough, a patient enough, and a united enough species, we will find a way to meet these challenges, to build our starships, and to begin our own human journey into the vast, beautiful, and timeless night. The concept of simultaneity, the idea of two events happening at the same time, seems so simple and intuitive in our everyday lives. But in the strange and beautiful world of Einstein's relativity, it is a concept that is revealed to be a profound illusion. The relativity of simultaneity is a direct and unavoidable consequence of the constancy of the speed of light, and it is a concept that shatters the very foundation of our classical, Newtonian worldview, the idea of a single, universal, and absolute now. To understand this, Let's return to our thought experiment of the high-speed train. An observer, let's call her the train observer, is standing at the exact midpoint of a long railway carriage, at the very moment that she passes an observer on the platform observer. Two lightning bolts strike the two ends of the carriage simultaneously, from the perspective of the platform observer. The platform observer is equidistant from the two strikes, and so the light from each strike will reach him at the same instant. For him, the two events are undeniably simultaneous. But what does the train observer see from her perspective? She is moving towards the point where the front lightning bolt struck, and away from the point where the rear lightning bolt struck. Since the speed of light is the same for her as it is for the platform observer, she will see the light from the front strike before she sees the light from the rear strike. For her, the two events are not simultaneous. The front lightning bolt struck first. So, who is right? The platform observer, who says the events were simultaneous, or the train observer, who says the front strike happened first? The profound and revolutionary answer of relativity is that they are both right. There is no absolute, objective fact of the matter about whether the two events were simultaneous or not. Simultaneity is not a property of the events themselves. It is a property of the frame of reference of the observer. Each observer, moving at a constant velocity, has their own unique slice of spacetime that they perceive as the present moment. And the slices of two observers who are in motion relative to each other are tilted with respect to one another. This has staggering philosophical implications. It means that there is no universal now. The idea of a single, cosmic present moment that is shared by everyone, everywhere, is a fiction of our classical intuition. My now is not the same as the now of an observer in a distant galaxy who is moving relative to me. In fact, what I consider to be my present moment could be in the distant past or the distant future for that other observer. This leads to the block universe picture of reality, the idea that the entire history of the universe past, present, and future is a single, timeless, four-dimensional block of space-time. The flow of time is an illusion, a trick of our consciousness as it moves along its own, personal world line through this pre-existing block. In this picture, the future is not open and unwritten, it is already there, in the same way that a distant city is already there, even if we have not yet arrived. This is a vision of reality that is deeply challenging to our notions of free will and of an open, creative future. But it is a vision that is a direct and logical consequence of the simple and experimentally verified principles of special relativity. The relativity of simultaneity is not just an abstract philosophical puzzle. It is a real physical feature of the universe we inhabit. And it is a profound and humbling reminder that our own subjective experience of a single, flowing, universal now is not a direct perception of reality, but is a powerful and useful, but ultimately limited, construction of our own, human consciousness. The dream of colonizing other worlds, of establishing a permanent and self-sustaining human presence on an exoplanet in another solar system, is one of the grandest and most ambitious visions of our long-term future. And it is a vision that is deeply and inextricably intertwined with the strange and beautiful physics of time dilation. An interstellar journey to a nearby star system. Even with the most advanced propulsion systems we can currently imagine, will be a journey that takes many decades and perhaps even centuries of Earth time. But for the colonists on board the starship, traveling at a significant fraction of the speed of light, the journey would be much shorter. They would arrive at their new home having aged by only a fraction of the time that has passed on Earth. This creates a profound and poignant temporal disconnect between the new colony and its home world. The first generation of colonists would be, in a very real sense, time travelers, exiles from their own time, starting a new branch of human history in a distant future. The communication between the new colony and Earth would be a so patient and generational affair. A message sent from the colony would take years to reach Earth, and the reply would take years to return. The two worlds would be connected by a thin, tenuous thread of light, their conversations unfolding on the timescale of human history, not of human lives. The colonists would read about the history of an Earth that they never knew, a history that unfolded while they were in the timeless, relativistic sleep of their long journey. And the people of Earth would look up at the night sky, at the faint, distant star that is now home to their descendants, and they would see not a present reality, but a ghost from the past, the light from the colony having taken years to cross the interstellar gulf. The new colony itself would have a different relationship with time. Their year zero would be the moment of their arrival. Their history would be a new one, written on a new world, and their connection to their home world would be a strange and beautiful one, a connection to a past that is also, in a sense, their future. And what of the exoplanet itself? If it orbits a more massive star, or if it has a stronger gravitational field than Earth, then the colonists would also be subject to gravitational time dilation. Their clocks would tick slightly slower than the clocks of their cousins who remained in deep space. Over many generations, this could lead to a measurable, and perhaps even significant, difference in the rate of aging and the perception of time between different branches of a future interstellar human civilization. The story of the colonization of an exoplanet is not just a story of technological and biological adaptation. It is also a story of a deep temporal and psychological adaptation. It is a story of a species that is learning to live with the profound and beautiful consequences of Einstein's revolution. A species that is learning to see time not as a single, universal river, but as a vast, branching delta, with a multitude of different currents, all flowing into the great, unknown ocean of the future. The challenges are immense, the timescales are vast, and the outcome is uncertain. But it is a story that speaks to the deepest and most enduring aspects of the human spirit, our courage, our curiosity, and our unquenchable desire to reach for the stars and to find a new home in the vast and wonderful expanse of the cosmos. The process of simulating the strange and counterintuitive effects of time dilation in a laboratory on Earth is a testament to the incredible ingenuity and precision of modern experimental physics. We cannot, of course, build a spaceship that can travel at near light speed, but we can create and study systems that are subject to the same relativistic laws. Systems that allow us to test the predictions of Einstein's theory with a level of accuracy that is almost beyond belief. The primary tool for this is the particle accelerator. In a machine like the Large Hadron Collider at CERN, subatomic particles, like protons, are accelerated to speeds that are just a tiny fraction below the speed of light. At these incredible velocities, the Lorentz factor is enormous. For a proton at the LHC, the gamma is about 7,000. This means that time for the proton is dilated by a factor of 7,000. From our perspective in the laboratory, the proton's internal clock is ticking 7,000 times slower than our own. This has a direct and measurable consequence for the unstable particles that are created in the collisions. Many of these particles have incredibly short lifetimes, and at rest, they would decay long before they could travel any significant distance. But because of their immense time dilation, their lifetimes are stretched by a factor of 7,000, which allows them to travel for many meters through the massive detectors before they decay. The very design and operation of these detectors is a constant, real-time confirmation of the reality of time dilation. We can also simulate the effects of gravitational time dilation in the laboratory, using incredibly precise atomic clocks. As we have seen, these clocks are so stable that they can measure the tiny differences in the flow of time caused by a change in altitude of just a few centimeters. In a sense, by simply lifting an atomic clock from the floor to a tabletop, you are performing an experiment in general relativity. Scientists are now developing even more precise nuclear clocks, which would use the transition frequency of a nucleus rather than an atom. These nuclear clocks could be up to 100 times more stable than the best current atomic clocks, which would allow us to test the effects of general relativity with an even greater precision, and to search for tiny, and as yet undiscovered, violations of Einstein's theory that could be a clue to a new, deeper theory of quantum gravity. Another, more exotic, way to simulate the effects of relativity is through analog systems. These are laboratory systems, like a flowing fluid or a Bose-Einstein condensate, that are designed to have mathematical equations of motion that are analogous to the equations of general relativity. By studying the behavior of waves in these systems, it is possible to create an analog of a black hole event horizon, or even to observe the analog of Hawking radiation. While these are not real black holes, they are powerful tools for testing the theoretical predictions of general relativity in a controlled laboratory environment. The simulation of relativistic effects is a beautiful and powerful example of the scientific method at work. It is a process of taking an abstract mathematical theory, deriving a set of precise quantitative predictions, and then devising a clever and ingenious experiment to test those predictions against the reality of the physical world. And in the case of relativity, every single one of these tests, from the largest particle accelerator to the most delicate atomic clock, has confirmed the strange, beautiful, and profoundly true nature of Einstein's vision of space, of time, and of gravity. The concept of time dilation, with its revelation that time is not a universal constant, but a fluid and observer-dependent quantity, has a profound and far-reaching impact that extends beyond the realm of physics and into the very heart of our cultural and philosophical understanding of the world. It is a concept that challenges some of our most deeply ingrained assumptions about the nature of reality, of identity, and of our own human experience. At the most fundamental level, time dilation forces us to confront the fact that our everyday intuitive perception of the world is a powerful, but ultimately limited, illusion. We experience time as a single, linear, and forward-moving river, a river that carries all of us along at the same speed. But this is a fiction of our macroscopic, low-speed, and low-gravity existence. The universe, at its deepest level, operates on a different, and much stranger, set of rules. This can be a source of deep philosophical unease. If there is no universal now, if my present moment is in the past of a distant, receding galaxy, what does that mean for our sense of a shared reality? If my future is already there in the block universe, what does that mean for my sense of free will? These are questions that do not have easy answers, questions that have been the subject of a long and rich dialogue between physicists and philosophers. But time dilation can also be a source of profound wonder and a new kind of spiritual or existential insight. The idea that time is not a rigid external master, but is a flexible and participatory aspect of reality, can be a deeply liberating one. It resonates with the teachings of many mystical and contemplative traditions, which have long held that our ordinary experience of linear time is a construction of the mind, and that it is possible, through certain states of consciousness, to access a more timeless, more holistic, and more fundamental level of being. The phenomenon of time dilation also has a powerful impact on our cultural narratives, particularly in the realm of science fiction. The trope of the interstellar traveler who returns home to find that centuries have passed is a powerful and poignant one, a story that allows us to explore some of our deepest human themes: the nature of love and loss, the relationship between the individual and society, the meaning of home, and the bittersweet price of exploration. These stories are not just entertaining fantasies, they are modern myths, a way for our culture to grapple with the profound and often unsettling implications of our new relativistic worldview. And at a more personal, psychological level, the concept of time dilation can be a powerful metaphor for our own subjective experience. We all know what it feels like for time to stretch and to contract. The flow state of deep, creative immersion, the timeless moment of a profound, loving connection, the eternal second of a life-threatening crisis. These are all experiences where our inner psychological time seems to detach from the external, clock time of the world. Time dilation, in this sense, is not just a feature of the physical universe. It is a feature of the universe of our own minds. The discovery of time dilation is one of the great intellectual and cultural achievements of our species. It is a testament to our ability to see beyond the limitations of our own everyday perception and to glimpse a deeper, stranger, and more beautiful reality. And it is a concept that will continue to challenge, to inspire, and to transform our understanding of ourselves and our place in the grand, mysterious, and wonderfully relativistic drama of the cosmos. The development of advanced propulsion technologies is the key that will unlock the next great era of space exploration, and it is a field that is currently buzzing with a host of new and exciting ideas, from the near-term and practical to the far-term and wildly speculative. At one end of the spectrum, we have the ongoing refinement of our current workhorse technologies. Chemical rockets are becoming more efficient, more reliable, and with the advent of reusability, dramatically cheaper. Electric propulsion systems, like ion thrusters and Hall thrusters, are becoming more powerful and more long-lived, making them the ideal choice for a new generation of ambitious robotic missions to the outer solar system and beyond. And nuclear thermal propulsion, the concept of using a fission reactor to heat a propellant, is experiencing a major renaissance, with NASA now actively developing a flight-ready engine that could cut the travel time to Mars in half. But the true long-term future of space propulsion lies in the technologies that can offer a quantum leap in performance. Technologies that can break the tyranny of the rocket equation and can open up the entire solar system to rapid, routine, and sustainable exploration. Nuclear fusion is, of course, the leading candidate in this category, but there are other, even more exotic possibilities. Antimatter propulsion is one such idea. Antimatter is the mirror image of ordinary matter, and when a particle of matter and a particle of antimatter meet, they annihilate each other in a burst of pure energy, converting 100% of their mass into energy according to E equals mc squared. This is, by far, the most efficient energy source known to physics. An antimatter engine, which would use the energy from these annihilations to heat a propellant or to create a beam of high-energy particles, would be an incredibly powerful and efficient propulsion system. The problem is that antimatter is incredibly difficult and expensive to produce, and even more difficult to store. We can currently only produce it in tiny nanogram quantities in our largest particle accelerators, and storing it requires a complex and power-hungry system of magnetic traps. Antimatter propulsion, for now, remains a technology for a very distant future. Solar sails are another, more near-term, but equally elegant, concept. A solar sail is a large, thin, and highly reflective membrane that is propelled by the gentle, but constant, pressure of sunlight itself. The photons from the sun, while massless, carry momentum. And when they bounce off the sail, they transfer a tiny amount of this momentum to the spacecraft. The thrust is minuscule, but because it is constant and requires no propellant, a solar sail can, over time, build up to a very high speed. This technology is particularly well suited for missions to the inner solar system, and for missions that require a lot of delta V, or change in velocity, like a mission to hover over the poles of the sun. More advanced versions of this concept include laser sails, where a powerful laser beam from Earth or from an orbiting power station would be used to push a much smaller and lighter sail, potentially accelerating it to a significant fraction of the speed of light for a fast interstellar flyby mission. And then there are the truly speculative, breakthrough propulsion concepts, the ideas that would require a new physics beyond our current understanding. The Alcubierre warp drive, which we have touched upon, is one such idea. It is a solution to Einstein's equations of general relativity that allows for faster-than-light travel, not by moving through space, but by moving with space, by creating a bubble of space-time that contracts space in front of it and expands space behind it. While mathematically consistent, it is thought to require a form of exotic, negative energy density matter that may not exist in nature. The future of propulsion technology is a rich and diverse landscape of ideas, a testament to the boundless creativity of the human mind, and it is a future that will be shaped by the choices we make, by the investments we decide to pursue, and by the new discoveries that are waiting to be made in the fundamental nature of space, of time, and of energy. The prospect of human travel to distant star systems, the ultimate dream of space exploration, is a challenge that is so immense that it forces us to confront the very limits of our science, our technology, and our own human biology. It is a journey that would be measured not in months or years, but in decades, in centuries, and perhaps even in millennia. And it is a journey where the strange and beautiful physics of time dilation would be not just a theoretical curiosity, but a central and defining feature of the human experience. As we have seen, a spacecraft traveling at a significant fraction of the speed of light would experience time at a much slower rate than a stationary observer on Earth. This is the key that could, in principle, make an interstellar journey possible within the lifetime of a human crew. But the price of this time travel into the future would be a profound and irreversible disconnection from the home world. The crew would become a lost tribe, a nomadic culture of the void, their only connection to their past, a series of increasingly ancient and irrelevant messages from a world that has moved on without them. The psychological and social challenges of such a multi-generational journey are almost impossible to fully comprehend. How would a society function in a small, enclosed, and completely isolated environment for centuries? How would a sense of purpose be maintained across generations that are born, live, and die in the deep, dark emptiness between the stars? These are questions that are as much for the sociologist and the psychologist as they are for the physicist and the engineer. The biological challenges are equally daunting. The human body is a product of 1 billion years of evolution in the specific, and in many ways, gentle, environment of the Earth. It is not designed for the harsh realities of deep space. The constant bombardment of galactic cosmic radiation would be a major, long-term health risk, increasing the likelihood of cancer, of cataracts, and of degenerative diseases of the central nervous system. A starship would need a massive and likely very heavy radiation shield, perhaps a thick shell of water ice or a powerful active magnetic field, to protect its crew. The absence of gravity would be another major challenge. While a constant thrust fusion engine could provide a continuous artificial gravity, any period of coasting would expose the crew to the debilitating effects of weightlessness. And a multi-generational mission would need to be a completely self-sustaining, closed-loop ecosystem, a tiny, artificial biosphere that can provide its crew with air, water, and food for centuries, without any possibility of resupply. This is a challenge that is on the very edge of our current understanding of ecology and life support technology. And then there is the destination itself. An interstellar mission would be a journey into the complete unknown. We can study a nearby star system from afar. We can detect the presence of planets. We can even analyze the composition of their atmospheres. But we can never know, for sure, what we will find until we get there. The planet that looks like a beautiful, blue-green, habitable world from a distance of 4 light-years could turn out to be a toxic and hostile environment. The interstellar explorers would be true pioneers, venturing into a new and uncharted territory with no guarantee of safety and no possibility of a quick return. The challenges of interstellar travel are so great that they can seem insurmountable, but they are also a powerful and inspiring vision, a vision that can pull us forward and can motivate us to solve the great challenges we face here on Earth. The technologies we will need to build a starship, a closed-loop ecosystem, a clean and abundant energy source, a deep understanding of human biology and psychology are the very same technologies we will need to build a sustainable and thriving civilization on our own planet. In a very real sense, the journey to the stars begins at home. The story of our scientific understanding of the universe is a story of a constant and often humbling expansion of our horizons. And at every step of this journey, we have been confronted with the limits of our own knowledge, with the vast and often surprising territory that lies beyond the well-lit circle of what we know. The current era of cosmology is no exception. We live in a time of incredible progress, of unprecedented precision in our measurements of the cosmos. And yet, this progress has not led to a sense of finality, but has instead revealed a new and even deeper set of mysteries, a new and even vaster landscape of the unknown. The nature of dark matter and dark energy is, of course, the most significant of these. The fact that 95% of the energy density of our universe is made of stuff that we do not understand is a profound and humbling statement about the current state of our knowledge. It is a sign that our current standard model of cosmology, while remarkably successful, is profoundly incomplete. The search for the identity of these dark components is the single greatest challenge in modern cosmology, and its resolution will likely require a new revolution in our understanding of fundamental physics. The problem of the beginning of the universe is another deep and enduring mystery. The Big Bang Theory is a powerful and well-tested description of the universe's evolution from a hot, dense state. But it cannot tell us what happened at the very beginning, at the moment of the singularity itself. To understand this ultimate origin story, we will need a full theory of quantum gravity, a theory that can unite the two great pillars of modern physics, general relativity and quantum mechanics. The quest for this theory is the holy grail of theoretical physics, a quest that has been going on for over half a century and that has led us into the strange and beautiful, but as yet unverified, worlds of string theory, of loop quantum gravity, and of extra dimensions. The nature of consciousness, as we have seen, is another profound mystery that seems to be deeply intertwined with the fundamental nature of reality. The hard problem of consciousness, the question of how a physical system like the brain can give rise to subjective experience, is a problem that challenges the very foundations of our materialistic worldview. And the role of the observer in quantum mechanics hints at a deep and enigmatic connection between the mind and the cosmos, a connection that our current science is only just beginning to grapple with. And beyond these known unknowns, there are surely unknown unknowns, mysteries that are so far beyond our current conceptual framework that we do not even know how to ask the right questions yet. The history of science is a history of surprises, of unexpected discoveries that have completely overturned our most cherished and long-held beliefs. There is no reason to think that this process has come to an end. The universe is not just stranger than we imagine. It is likely stranger than we can imagine. This is not a cause for despair or for a retreat into dogma. It is, on the contrary, a cause for profound excitement and for a deep sense of intellectual humility. It is a reminder that the scientific journey is not a journey towards a final, complete, and closed book of knowledge, but is an endless and open-ended adventure of discovery. And as we stand on the shore of this vast cosmic ocean of the unknown, we are equipped with the most powerful tool for exploration that has ever been devised, the scientific method, with its cycle of observation, of hypothesis, of prediction, and of testing. It is a tool that is not about finding final, absolute truths, but is about a constant process of refining our understanding, of building better and better maps of the mysterious and beautiful territory of reality. The journey is the destination, and the quest itself, the shared human endeavor to understand our cosmic home, is a source of meaning, of purpose, and of a deep and abiding sense of wonder. And as you lie on the threshold of sleep, as your own individual consciousness prepares to embark on its own nightly journey into the mysterious and uncharted territory of the unconscious, you can feel a sense of participation in this grand, human, and cosmic adventure. Imagine waking up one day to a world that feels both deeply familiar and utterly strange. A reality where the solid ground beneath your feet and the steady forward march of time are revealed to be just the tip of a cosmic iceberg. What if everything you see, every choice you make, and every fleeting moment you experience are not isolated events, but fragments of a much grander, more intricate, and largely unseen structure? This is the world we are about to explore together, a universe not confined to the familiar three dimensions of our senses, but one that stretches into realms that defy our intuition and challenge our imagination. At first glance, our lives seem straightforward enough. We exist in a space defined by three coordinates. We can move left and right, up and down, forward and backward. And we are carried along by a fourth dimension, the relentless current of time, which pushes us ever onward from the past, through the present, and into an unknown future. But as science has delved deeper into the nature of reality, it has uncovered a set of rules that seem to border on magic, a subatomic realm where the common sense of our macroscopic world dissolves into a shimmering sea of probability and potential. This is the world of quantum physics, a world where particles can be in many places at once, where the very act of observation seems to shape the reality being observed, and where the linear flow of time itself may be nothing more than a stubborn illusion. To begin this journey, let us start with the simplest of concepts, a single, dimensionless point. It has no length, no width, no depth. It is a pure, abstract location. Now, connect two such points, and you have a line. The first dimension, a world of pure length, at a second direction, perpendicular to the first, and you create a plane, a two-dimensional world of length and width, like the surface of a sheet of paper. This is the world of geometry, of squares, circles, and triangles. And if you take this two-dimensional plane and fold it, pulling it up into a third direction, you create the three-dimensional space that we call home, a world of solid objects with length, width, and height. This progression seems intuitive enough, but what happens if we continue this pattern? What lies beyond the familiar three dimensions of our physical world? This is where our journey into the strange and beautiful landscape of modern theoretical physics truly begins. The first step beyond our spatial reality is into the fourth dimension, a concept that is most commonly, and perhaps most intuitively, understood as time. In this picture, time is not just a fleeting, intangible flow, but a dimension akin to space. Our entire existence, from the moment of our birth to the moment of our death, can be visualized as a single, four-dimensional object, a world line or a space-time worm snaking its way through the unified fabric of space-time. Your past, your present, and your future all exist simultaneously in this block universe, and your consciousness is simply a spotlight, a point of awareness, moving along this pre-existing, four-dimensional reality. But what if this single, linear timeline is not the only one. What if every choice we make, every random quantum event in the universe, causes reality to split, to branch off into a new, parallel timeline? This is the gateway to the fifth dimension. The fifth dimension is not a new direction in space, but a new direction in the landscape of possibility. It is the dimension that contains all the alternate histories, all the what-ifs, all the different paths that our universe could have taken, branching out from every moment of choice. There is a timeline where you took that job, and a timeline where you did not. A timeline where the dinosaurs never went extinct, and a timeline where they evolved into intelligent, sentient beings. The fifth dimension is the space of these branching possibilities, a vast, ever-growing tree of alternate realities. As we ascend further up this dimensional ladder, the concepts become increasingly abstract, moving from the realm of physics into a space that feels closer to metaphysics. The sixth dimension allows us to not just conceive of these branching timelines, but to fold the space of possibilities itself. It is a dimension that would allow for a kind of shortcut between different, seemingly distant branches of the multiverse. It is the plane that contains all the possible histories that could have arisen from the same initial conditions of our Big Bang. A complete, phase space of our specific kind of universe. The seventh dimension marks an even more profound leap. It is the dimension that contains the set of all possible universes that could have started with different initial conditions. This is the realm of universes with different physical laws, different fundamental constants, different numbers of spatial dimensions. It is a library of all possible cosmic beginnings, each one giving rise to its own unique, six-dimensional tree of possibilities. The eighth dimension is the plane that contains all of these different cosmic libraries, allowing for a comparison, a branching between these fundamentally different kinds of realities. The ninth dimension takes this to its logical extreme. It is the dimension that contains all possible physical laws, all possible initial conditions, all possible histories, all at once. It is the ultimate ensemble, the set of all possible universes. And finally, we arrive at the 10th dimension, in the conceptual framework of string theory, the leading candidate for a unified theory of everything. The universe has 10 spatial dimensions and one of time. The extra 6 dimensions beyond our familiar 3 are thought to be compactified, curled up into a tiny, complex geometrical shape at every point in our space. But in a more conceptual, hierarchical sense, the 10th dimension can be thought of as the ultimate point of origin, a dimensionless point of pure potential from which all the lower dimensions, all the possibilities, all the universes emerge. It is the everythingness that contains all possible realities, a concept so vast, so all-encompassing, that it transcends our ability to visualize or even fully comprehend. This journey through the dimensions is not just a mathematical game. It is a profound and humbling exploration of the potential richness and complexity of reality. It suggests that the universe we experience, with its familiar 3 dimensions and its steady forward-moving time, may be just a single, thin slice of a much grander, multidimensional, and endlessly fascinating cosmic structure, a structure whose deepest secrets are hidden in the unseen, and perhaps unknowable, dimensions that lie just beyond the horizon of our perception. The strange and counterintuitive world of quantum mechanics provides another, equally profound, challenge to our classical common-sense understanding of reality. At the subatomic level, the very fabric of existence seems to be woven from threads of uncertainty, of probability, and of a deep participatory relationship between the observer and the observed. The solid, definite world of our everyday experience dissolves into a shimmering, ghostly sea of potential. The fundamental constituents of our universe, the particles that make up every atom in our bodies, are not solid, billiard ball-like entities. They exist as waves of probability. their properties not fixed and definite, but existing in a superposition of all possible states at once until the moment of measurement. And it is this act of measurement, of observation, that seems to be the magical ingredient that collapses this wave of potential into a single, definite reality. This raises one of the most profound and unsettling questions in all of science. Are we, in some sense, creating reality by the very act of observing it? If a particle does not have a definite position until we look at it, then what does it mean to say that it exists? Before our observation, this is a question that has divided physicists for a century, leading to a host of different and often bizarre interpretations of the quantum world. Some physicists take a pragmatic view, arguing that these quantum effects, while real and measurable in the subatomic realm, are confined to that realm, a process known as decoherence. The constant interaction of a quantum system with its environment is thought to rapidly destroy the delicate superposition of macroscopic objects, ensuring that the classical world of our everyday experience remains stable and predictable. The quantum possibilities are still there, but they have faded into the background, their interference effects washed out by the noise of the environment, leaving us with a single, coherent, classical reality. But others have been drawn to more radical conclusions. The many worlds interpretation, for example, proposes that the wave function never truly collapses. Instead, every quantum measurement causes the entire universe to split into multiple, parallel branches, with each branch corresponding to one of the possible outcomes. In this view, we are not collapsing reality. Our observation is simply entangling us with one particular branch of a vast, ever-growing multiverse. We are not creating a single reality. We are choosing our path through an infinite, pre-existing tapestry of all possible realities. This is like tuning a radio. All the other stations are still broadcasting, but we are only experiencing the one we have locked onto. This line of thought leads to even deeper and more perplexing questions. If observation is the key to actualizing reality, then who or what was the first observer? What existed before the emergence of life, of consciousness, in the universe? Did the cosmos exist for billions of years as an uncollapsed, ghostly sea of pure potential, waiting for a conscious mind to come along and give it form? Or was there some other, more fundamental form of observation at play? A cosmic observer that has been collapsing the wave function since the very beginning. The relationship between observation and the flow of time is another area of deep mystery and speculation. We experience time as a relentless one-way arrow, moving from a fixed past to an open future. But what if this arrow of time is not a fundamental property of the universe, but an illusion, a story that our consciousness constructs? What if, at a deeper, multidimensional level, all of time past, present, and future exists simultaneously? In this block universe picture, the act of observation at a single point in time, the present moment, could be what creates the appearance of a consistent historical past leading up to that moment. It is a radical idea, the notion that our present awareness could, in a sense, retroactively create the billions of years of cosmic history that we observe. It is as if, from the ultimate vantage point of the 10th dimension, a single choice, a single act of observation, collapses not just a present state, but an entire, consistent, four-dimensional space-time history. This is a concept that strains the limits of our language and our logic, but it is one that is being seriously explored at the frontiers of theoretical physics. The very terms we use, observer, measurement, consciousness, are laden with philosophical baggage. For some, the role of the observer is synonymous with the role of a creator, or even of God. The idea that a divine cosmic mind is constantly observing and therefore creating. The universe is a powerful and enduring one that is found in many of the world's spiritual traditions. From a scientific perspective, this is not a testable hypothesis. But the parallels between these ancient metaphysical ideas and the strange, participatory reality suggested by quantum mechanics are undeniably fascinating. They suggest that we may be on the verge of a new synthesis, a new understanding of reality that can bridge the long-standing gap between the inner world of subjective experience and the outer world of objective science. What is clear is that the simple, mechanistic picture of a universe that exists out there, independent of our own minds, is no longer tenable. We are not separate from the reality we observe. We are deeply and mysteriously intertwined with it. The act of attention, of awareness, is not a passive process. It is a creative, world-shaping force. And the question of how far this power extends, of what other hidden layers of reality might be accessible to a new and more refined form of consciousness, is perhaps the most exciting and profound adventure that humanity has ever embarked upon. The familiar intuitive experience of time as a steady, unidirectional flow, a relentless arrow pointing from the past, through the present, and into the future, is one of the most fundamental, and yet most mysterious, aspects of our reality. The British astrophysicist Sir Arthur Eddington, in 1928, coined the evocative phrase, the arrow of time, to capture this powerful one-way nature of our temporal experience. We see glasses break, but we never see them spontaneously reassemble. We remember yesterday, but we have no direct knowledge of tomorrow. This seems so obvious, so deeply woven into the fabric of our existence, that we rarely stop to question it. And yet, when we look at the most fundamental laws of physics, this arrow of time is strangely absent. The equations of Newtonian mechanics, of Maxwell's electromagnetism, and even of Einstein's theory of relativity, are all time reversal symmetric. They work just as well for a process running forwards in time as for one running backwards. The laws themselves do not distinguish between the past and the future. So, if the fundamental laws are symmetric, where does the manifest asymmetry of our world come from? Why do we experience time as a one-way street? The standard answer lies in the second law of thermodynamics, which states that the total entropy or disorder of a closed system always increases over time. The universe began in a state of incredibly low entropy, a highly ordered and uniform state, and it has been evolving towards a state of higher entropy ever since. This provides a thermodynamic arrow of time, a statistical directionality that explains why systems in our universe tend to move from order to disorder. But this just pushes the question back a step. Why was the early universe in such a special, low-entropy state to begin with? This is one of the deepest unsolved problems in all of cosmology. But what if there is another, even more profound, layer to this mystery? What if the arrow of time is not just a property of the universe, but is intimately linked to the nature of life and consciousness itself? Consider a simple chemical reaction, where two molecules, A and B, combine to form a new molecule, C. We perceive this as a forward-moving process, but the underlying physical laws would allow, in principle, for the reverse reaction, for C to spontaneously break apart into A and B. In our observed reality, however, the forward reaction is overwhelmingly dominant. Why, some have speculated that the very emergence of life, the self-organizing processes that arose from the primordial soup billions of years ago, may have somehow selected a preferred direction of time. Perhaps the complex information processing systems that we call life can only maintain their delicate, low-entropy state by surfing the universal wave of increasing entropy. Life, in this view, is a process that creates local pockets of order by exporting disorder to its environment, a process that is fundamentally tied to the thermodynamic arrow of time. But this leads to a fascinating and deeply speculative thought experiment. If the emergence of life is somehow linked to the arrow of time, could there be other forms of life in other corners of the cosmos, or perhaps even in a parallel universe, that have evolved in a universe with a reversed arrow of time? What would such a reverse time life form be like? To us, its actions would appear to be a bizarre reversal of causality. Its effects would precede its causes. A shattered cup would reassemble in its hands, and then it would place the whole cup on the table. It would be born old and die young. Communication with such a being would be a logical impossibility, a dizzying paradox of crossed causalities. The science fiction trope of a backward-flowing timeline provides a powerful way to explore these conceptual puzzles. Imagine an alien civilization whose history unfolds in reverse relative to our own. Their arrival on Earth in our year 3000 would be, from their perspective, the beginning of their historical interaction with us, their subsequent conquest of the planet, which from our perspective would look like a slow, inexplicable retreat, would be, for them, a story of glorious expansion. Who, in this paradoxical encounter, is the victor? The question itself dissolves into meaninglessness. The very framework of a shared, linear narrative breaks down. While this is a highly speculative scenario, it is one that is not entirely disconnected from the frontiers of theoretical physics. The idea of a mirror universe, a universe where the laws of physics are a mirror image of our own, including a reversed arrow of time, has been seriously proposed as a potential solution to some of the puzzles of cosmology, such as the nature of dark matter. In this picture, our universe and this mirror universe could have been born together in the Big Bang, moving in opposite directions in time from a common origin. The ultimate nature of time may be even stranger than these scenarios suggest. The block universe view, which arises from Einstein's theory of relativity, suggests that all of time past, present, and future exists simultaneously as a single, four-dimensional spacetime manifold. In this view, the flow of time is an illusion, a product of our consciousness moving through this pre-existing static block. If this is the case, then the arrow of time is not a property of the universe itself, but a property of our perception. Perhaps our brains are wired in such a way that we can only process information sequentially, creating the subjective experience of a flowing now that moves from a remembered past to an anticipated future. But what if this is just one possible mode of consciousness? Could there be other forms of awareness that could perceive the block universe in a different way, that could access the past and the future with the same ease that we access different locations in space? And what if, at an even deeper, multidimensional level, the very concept of a single timeline, whether forward or backward, is an oversimplification? In the higher dimensional reality suggested by some theories, our entire four-dimensional spacetime could be just one slice of a much larger, more complex structure, a structure that contains all possible timelines, all possible histories, all at once. From this ultimate, atemporal perspective, the distinction between forward and backward, between cause and effect, might cease to have any meaning. It would be like looking at a complex, woven tapestry. From the perspective of a single thread, there is a clear, linear path. But from the perspective of the whole, there is only the intricate, beautiful, and timeless pattern of the weave itself, the arrow of time, which feels so fundamental and unshakable to us, may be just a local, emergent, and perhaps even illusory feature of our particular corner of a much grander and much stranger cosmic reality. Imagine a reality where every decision you have ever made, every path you have ever taken, and every possibility you have ever considered, all exist simultaneously, woven into the vast, multi-dimensional fabric of existence. This is a universe where the simple, binary logic of yes or no, of this or that, becomes the fundamental building block of an infinitely complex and beautiful cosmic structure. This binary viewpoint is not a formal scientific theory, but a powerful conceptual framework, a lens through which we can begin to grasp the mind-bending implications of modern physics, from the quantum world to the highest, most abstract dimensions of reality. It is a way of seeing the universe not as a collection of things, but as a cascade of choices, a story written in the simple yet profound language of binary decisions. At its heart, this viewpoint suggests that the universe, in its most fundamental state, is a realm of pure, unmanifest potential. The Big Bang, the moment we perceive as the beginning of our cosmos, can be reimagined not as a random, chaotic explosion, but as the first great binary toggle. The first yes in an infinite sea of no. It is the moment when the universe chose existence over non-existence, something over nothing. This single, primordial choice unleashed a cascade of subsequent bifurcations, a torrent of binary decisions that have shaped the evolution of our reality ever since. The theory of cosmic inflation, with its period of hyper-accelerated expansion in the first fraction of a second, aligns beautifully with this picture. It can be seen as the rapid, exponential unfolding of the possibilities contained within that first binary moment, the unfurling of the cosmic blueprint that was encoded in that initial choice. From this ultimate, atemporal perspective, the very concept of a before the Big Bang is transformed. It is not a question of what existed in a preceding time, but of what existed in a state of uncollapsed, pre-binary potential. It is a journey backward not in time, but into a realm of pure, undifferentiated indeterminacy. A shimmering fog of possibility waiting for the first creative act of distinction, the first yes or no, to give it form. This binary, decision-based framework is not just a feature of the cosmos. It is a fundamental feature of our scientific inquiry itself. The history of science is a history of branching paths, of competing interpretations of the same data. Isaac Newton's laws of motion and gravity provided a powerful and precise framework that reigned for centuries. But when Albert Einstein introduced his theory of general relativity, which described gravity not as a force, but as the curvature of a dynamic spacetime, he did not render Newton's laws wrong. He offered a new, deeper, and more comprehensive interpretation of the same phenomena. Newton's theory became a collapsed state, a highly accurate approximation that works perfectly well in the low-gravity, low-velocity regime of our everyday experience. Einstein's theory represents a different branch of the possibility space, a different way of looking at the same cosmic rhythm. The two theories are not mutually exclusive in a simple, binary sense. They are two different and complementary layers of a single, multi-layered truth. We see the same pattern in the development of our understanding of matter. The classical picture of solid, point-like particles gave way to the quantum picture of wave-particle duality. And string theory, in its most ambitious form, seeks to unify these different pictures by proposing that the fundamental constituents of reality are neither particles nor waves, but tiny, vibrating strings of energy. Each of these theoretical shifts is not a negation of what came before, but an expansion of the possibility space, a new and more nuanced way of interpreting the fundamental binary choices that seem to govern the cosmos. This leads us to a profound and unsettling question about our own place in this branching. Decision-based reality. If every quantum event, every choice, creates a new timeline, a new branch of the multiverse, then where are we? The many worlds interpretation of quantum mechanics suggests that we are on all the branches at once, that there are an infinite number of us, each living out a different reality. But our subjective experience is one of a single, continuous, and coherent life. Why do we perceive only this one particular path through the infinite, binary forest of possibilities? The answer may lie in the nature of consciousness itself. Perhaps our consciousness, our point of awareness, is the very thing that navigates this multidimensional landscape, collapsing the wave function of our own experience into a single, linear narrative. We are the thread that is being woven through the tapestry, and the path we take is the story of our lives. This brings us to the ultimate paradox, the tension between free will and determinism. If all possible outcomes exist somewhere in the multiverse, then what is the meaning of our choices? The binary viewpoint offers a fascinating, if speculative, resolution. It suggests that while all paths may exist in a state of potential, our consciousness, through the act of choice, is what makes a particular path real for us. The universe, in this picture, is deterministic in that all possibilities are governed by the underlying mathematical laws of the wave function. But we experience free will because our consciousness is the agent that chooses which of these deterministic paths to actualize, to experience as our reality. We are both the characters in a pre-written play, and the audience that, by its very attention, brings a particular performance to life. This idea finds a powerful fictional expression in the works of authors like Philip K. Dick and Jorge Luis Borges, who constantly explore the nature of reality, of alternate histories, and of the power of the mind to shape its own experience. It is a vision of the universe that is both deeply mechanistic and profoundly magical. A universe where the rigid laws of physics and the creative freedom of consciousness are two sides of the same, fundamental, binary coin. The binary viewpoint is not a scientific theory in the traditional sense. It is a conceptual tool, a way of thinking, a new lens through which to view the mysteries of the cosmos. It invites us to see the universe not as a static, predetermined machine, but as a dynamic, interactive, and endlessly creative process, a process of constant becoming, a story that is being written, moment by moment, choice by choice, in the simple, yet infinitely profound, language of yes and no. And as we stand at the crossroads of our own lives, facing the infinite, branching possibilities of our own future, we can take some comfort in the idea that we are not just making a choice in the universe, but that our very choice is an act of creation, an act that helps to shape the very fabric of reality itself. At the heart of our existence lies a paradox that is both deeply personal and profoundly cosmic. The universe we inhabit appears to be exquisitely and improbably fine-tuned for the existence of life. From the strength of the force of gravity to the precise mass of the proton, the fundamental constants of nature seem to have been set to just the right values to allow for the formation of stable atoms, of long-lived stars, of planets with complex chemistry, and ultimately of conscious, questioning beings like ourselves. If any of these values were even slightly different, the universe would be a sterile and barren place. This apparent fine-tuning has led to a great deal of debate among scientists and philosophers. For some, it is the most compelling evidence we have for the existence of a divine creator, a guiding hand that has purposefully designed the cosmos with us in mind. But for many cosmologists, there is a more natural, if no less astonishing, explanation, the anthropic principle. In its simplest form, the anthropic principle is a statement of selection bias. It says that the reason we observe a universe that is hospitable to life is because we could not, by definition, observe one that was not. We are here to ask the question precisely because our universe is one of the rare, life-friendly ones. This principle gains its full explanatory power when it is combined with the idea of a multiverse. If there are countless, perhaps an infinite number of other universes, each with its own randomly assigned set of physical laws and constants, then it is no longer a surprise that at least one of them, by sheer chance, would have the right conditions for life. We are simply the winners of a cosmic lottery of unimaginable proportions. It is a powerful and elegant explanation, but it is one that relies on the existence of a vast and perhaps forever unobservable ensemble of other realities. The anthropic principle, in this context, becomes a kind of statistical inevitability. But it also raises a host of new and perplexing questions. If every possible outcome of every quantum event is realized in a separate branch of the multiverse, as the many worlds interpretation suggests, then what is the status of these other realities? Are they as real as our own? And why do we experience only this one, single, coherent timeline? The complexity of our own existence provides a powerful, if metaphorical, parallel to this cosmic puzzle. The human eye, for example, is a marvel of biological engineering, an instrument of such intricate and perfectly coordinated complexity that it can seem, at first glance, to be the product of intelligent design. How could such a thing have evolved through a series of random, unguided mutations? The answer, of course, is the power of natural selection acting over immense geological timescales. But the anthropic principle offers a different kind of explanation, a different way of looking at the same improbability. It suggests that in the vast, multidimensional possibility space of all possible biological forms, the existence of a complex, image-forming eye is not improbable at all. It is a necessary condition for the emergence of an observer who can look up at the stars and wonder about the nature of reality. The eye and the universe it observes are part of a self-consistent, participatory loop. This brings us back to the binary viewpoint, the idea that reality is a cascade of choices. The Big Bang itself can be seen as the first great binary toggle, the choice of existence over non-existence. The subsequent period of cosmic inflation was the rapid unfolding of the possibilities contained within that initial choice. And every subsequent event, from the formation of the first atom to the evolution of the first living cell, can be seen as a further collapse of the universal wave function, a further selection of one path from an infinite, branching tree of possibilities. Our universe, with its specific set of laws and its capacity for life, is the result of a particular and very long sequence of yes-no decisions. The anthropic principle, in this light, is not just a statement about our universe. It is a statement about the nature of observation itself. Our consciousness, our ability to observe and to ask questions, is what collapses the vast, superpositional reality of the multiverse into the single, experienced reality of our timeline. We are not just living in a universe that is fine-tuned for us. We are, in a very real sense, the tuners. This is a radical and deeply challenging idea, one that places consciousness at the very center of the cosmic story. It suggests that the line between the subjective and the objective, between the mind and the world, is not as clear as we once thought. But what about the other timelines? The other universes where the cosmic dice roll came up differently? What about the universe where the laws of physics are slightly different, where JFK's assassination was thwarted, where a different sperm fertilized the egg that became you in the many worlds picture? These realities are all equally real, branching off from our own at every moment of choice. They are the might-have-beens that are somewhere else, the what-is. We can never access them. We can never know them directly. But the anthropic principle, combined with the multiverse, suggests that they are an integral part of the grand cosmic tapestry. Our reality is just one thread in this infinite weave. This is a vision that can be both humbling and liberating. It is humbling because it removes our own personal story from the center of creation. But it is also liberating because it opens up an infinite space for possibility, for creativity, for the endless, beautiful, and sometimes tragic unfolding of all that could ever be. And as we stand on the precipice of our own choices, we can do so with a new and profound sense of the weight and the wonder of our own creative participation in the grand and perhaps infinite drama of the cosmos. The concept of time travel, long a staple of science fiction, becomes a far more complex and philosophically charged endeavor when viewed through the lens of a multidimensional, branching reality. The classic paradoxes of time travel, like the famous grandfather paradox, are all predicated on the assumption of a single, linear, and mutable timeline. If you travel back in time and prevent your own grandfather from meeting your grandmother, you create a logical contradiction. If you were never born, then you could not have traveled back in time to do the deed in the first place. But in a universe governed by the principles of quantum mechanics and higher dimensions, the story is not so simple. The many worlds interpretation of quantum mechanics offers a clean, if mind-bending, solution to these paradoxes. When you travel back in time and alter a past event, you are not changing your own history. You are simply creating a new branch of the multiverse, a new parallel timeline. In this new timeline, you were indeed never born. But in your original timeline, the one you departed from, your journey into the past is simply a part of its history, and your absence is its future. You have not erased yourself. You have simply moved to a different branch of reality, becoming a kind of time orphan, forever disconnected from your own origins. The popular film Back to the Future plays with a hybrid of these ideas. Marty McFly's meddling in his parents' past causes him to start fading from existence, a visual metaphor for the paradoxes of a single timeline model. But the eventual outcome, a new and improved present, suggests a kind of timeline editing that is more in line with a branching reality. Another proposed solution to the paradoxes is the Novikov self-consistency principle, which posits that the universe is fundamentally paradox-proof. Any action a time traveler takes in the past was always a part of that past's history. You cannot change the past because your actions were already factored into the timeline that led to your own existence. You are not an editor of history, but a character in a script that has already been written. The film 12 Monkeys is a brilliant and tragic exploration of this idea. The protagonist's journey into the past is not an attempt to change it, but a futile and predetermined loop, where his actions are the very cause of the events he is trying to prevent. He is a ghost in his own history, unable to alter the inevitable unfolding of a fixed, four-dimensional block universe. These different models of time travel, the branching multiverse, the self-consistent loop, are all attempts to grapple with the deep, logical puzzles of causality in a universe where the past might be accessible. But the introduction of higher dimensions adds another layer of complexity and possibility. If our four-dimensional spacetime is just a brain floating in a higher dimensional bulk, as some theories suggest, then time travel might not involve moving backwards along our own timeline at all. It might involve taking a shortcut through the bulk, a wormhole that connects two distant points in our own space-time. This is the classic science fiction trope of a hyperspace jump, and it is an idea that has a tentative, if highly speculative, grounding in the mathematics of general relativity and string theory. But what about the 10th dimension, the conceptual point of origin that contains all possible realities, all possible timelines, all at once from this ultimate atemporal vantage point? The very concept of traveling through time loses its meaning. Past, present, and future are not a sequence to be traversed, but a single, unified, and timeless landscape. A time traveler, in this context, would not be a being moving from one moment to another. but a form of consciousness that could shift its point of awareness from one part of the block universe to another, experiencing different moments, different timelines, different realities, with the same ease that we shift our gaze from one object to another in a room. This is a level of reality that is far beyond our current comprehension, but it is a logical extension of the ideas we have been exploring. The binary viewpoint, with its cascade of yes/no decisions, provides a useful way to visualize this. Our experienced reality is one particular path through this infinite binary decision tree. A time traveler who changes the past is simply forcing a different branch to be taken at a particular node, creating a new, alternate history. But from the perspective of the entire tree, all branches coexist. Nothing is ever truly lost or changed. It is just a matter of which path is being followed, which story is being told. The paradoxes of time travel, then, are not necessarily logical contradictions that make it impossible. They are conceptual challenges that force us to expand our understanding of the nature of time, of reality, and of causality itself. They are a sign that our intuitive, linear, and single timeline view of the world is a profound oversimplification. The true nature of reality may be a far richer, more complex, and more wonderfully paradoxical tapestry of interwoven possibilities, a tapestry where every choice matters, and every path is, in some deep and mysterious sense, real. The quest to unify the fundamental forces of nature, to find a single, elegant theory that can describe all the phenomena of the cosmos, is the holy grail of modern physics, and the key to this quest may lie in the existence of unseen, higher dimensions. The story begins in 1919 with a remarkable letter sent to Albert Einstein by a little-known German mathematician named Theodor Kaluza. Kaluza had made a startling and beautiful discovery. He had found that if he took Einstein's equations of general relativity, which describe gravity as the curvature of a four-dimensional spacetime, and reformulated them in 5 dimensions, something magical happened. The equations naturally split into 2 parts. One part was the original, four-dimensional theory of gravity. The other part was, to everyone's astonishment, Maxwell's equations of electromagnetism. It seemed that the electromagnetic force, the force responsible for light, for electricity, for chemistry, was nothing more than the curvature of a hidden 5th dimension. This was a breathtakingly elegant and powerful idea. It suggested that the two seemingly disparate forces of gravity and electromagnetism were just different aspects of a single, unified 5-dimensional geometry. Einstein was initially captivated by the idea, and he helped Kaluza to get his paper published, but the theory had a problem. Where is this 5th dimension? We do not perceive it in our everyday lives. In the 1920s, the Swedish physicist Oskar Klein proposed a solution. He suggested that the 5th dimension is compactified, curled up into a tiny, microscopic circle at every point in our space, a circle so small that it is completely invisible to us. This Kaluza-Klein theory was a beautiful and revolutionary idea, the first serious attempt at a unified field theory, but it ultimately failed to be a complete theory of nature. It could not account for the other 2 known forces, the strong and weak nuclear forces, and it made some incorrect predictions about the properties of particles like the electron. But the core idea, that the fundamental forces of nature could be a manifestation of the geometry of hidden, extra dimensions, was a powerful one that would lie dormant for decades, only to be resurrected in the 1980s with the rise of string theory. String theory, in its modern form, requires the existence of not just 1, but 6 or 7 extra spatial dimensions to be mathematically consistent. And in this framework, the Kaluza-Klein idea is reborn in a much richer and more complex form. The different forces and particles we see in our universe are all determined by the intricate, multidimensional geometry of these curled-up Calabi-Yau spaces. This idea of a multidimensional reality is not just an elegant mathematical curiosity. It offers a potential, and deeply profound, explanation for some of the greatest mysteries of modern cosmology, the existence of dark matter and dark energy. Together, these two enigmatic entities make up 96% of the total energy density of our universe. The ordinary baryonic matter that makes up the stars, the planets, and ourselves is a mere 4%, a cosmic afterthought. We are living in a universe that is dominated by substances whose nature we do not understand. Dark matter is the invisible gravitational scaffolding of the cosmos. We see its effects in the rotation of galaxies and in the gravitational lensing of light, but we have never been able to detect the dark matter particle directly. Dark energy is the mysterious, repulsive force that is causing the expansion of the universe to accelerate. Its origin is a complete enigma. The idea of extra dimensions provides a new and tantalizing framework for thinking about these mysteries. In some brain world scenarios, the particles and forces of the standard model are confined to our three-dimensional brain, while gravity is free to propagate in the higher dimensional bulk. In this picture, dark matter might not be a new type of particle at all. It could be the gravitational influence of matter on a nearby parallel brain, a shadow universe separated from our own by a tiny distance in a fourth spatial dimension. We cannot see the matter on that other brain, but we can feel its gravity, leaking across the dimensions and creating the effects we attribute to dark matter. This is a speculative, but testable, idea. If dark matter is indeed a gravitational shadow from another dimension, it could lead to subtle, but detectable, deviations from standard general relativity on small scales, which could be searched for in high-precision laboratory experiments. Dark energy, too, could find a home in this multidimensional picture. It could be a manifestation of the energy of the bulk space itself, or a result of a force between our brain and other parallel brains. The accelerating expansion of our universe could be caused by the gravitational repulsion from a nearby massive brain in the extra dimensions. This would be a profound shift in our cosmological worldview. The destiny of our universe would not be determined by the matter and energy within it, but by its relationship with a larger, unseen, multidimensional reality. The concept of higher dimensions is one of the most exciting and mind-bending frontiers of modern physics. It is a frontier that is still largely theoretical, but it is one that holds the promise of a deeper, more unified, and more elegant understanding of the cosmos. It suggests that the reality we perceive is just a slice, a shadow, of a much richer and more complex multidimensional structure. And the great mysteries of dark matter and dark energy may not be mysteries about new substances in our universe, but clues that are pointing us towards the existence of new dimensions beyond our universe. The quest to find these hidden dimensions, whether through particle accelerators, gravitational wave detectors, or subtle cosmological observations, is one of the great adventures of 21st century science. An adventure that could one day reveal the true multidimensional glory of our cosmic home. The concept of control, the idea that we are the masters of our own destiny, is one of the most cherished and perhaps most illusory of all human beliefs. We strive for it. We celebrate it. We build our societies and our psychologies around it. And yet, when we look closely at our own lives, and at the world around us, we are constantly confronted with the limits of our own agency. The story of the person who, through sheer willpower, decides not to get sick, only to collapse with the flu the moment they take a vacation, is a familiar one. The anecdote of the cancer patient who visualizes their immune system attacking a tumor and experiences a miraculous remission is a powerful testament to the mind-body connection. But it is also a rare and exceptional event that is far from a controllable, reproducible technique. The 1993 Washington meditation experiment, where a large group of meditators seemingly reduced the city's violent crime rate through focused, collective intention, is a fascinating and provocative data point. But it is also a study that has been heavily criticized for its statistical methodology and its lack of adequate controls. These examples hint at a reality where our consciousness can have a subtle, but real, influence on the physical world. But they also highlight the profound difficulty of isolating, understanding, and harnessing this influence in a predictable and controllable way. The universe, it seems, is not a simple, linear system that responds directly to our individual will. It is a vast, complex, and interconnected web of influences. A system where our own personal intentions are just one small thread in an immense and intricate tapestry. The framework of higher dimensions provides a powerful and beautiful way to visualize this complex interplay between individual agency and the larger collective reality. In the five-dimensional model of branching timelines, every choice we make, every action we take, creates a new path through the possibility space. Our free will is real, in that we are the ones who are choosing which path to follow. But we are not choosing in a vacuum. Our choices are constantly being influenced, constrained, and shaped by the choices of every other conscious and even non-conscious entity in the universe. We are part of a vast, consensual reality, a shared timeline that is the result of a constant, dynamic negotiation between trillions of different wills and intentions. Imagine your life as a single line, oscillating up and down on a graph. The horizontal axis is time, and the vertical axis is your state of being, your happiness, your health, your success. You may desire to keep your line consistently high, to live a life of constant triumph and joy. But your line is not an independent entity. It is entangled with the lines of everyone around you, your family, your friends, your community, your society. Their choices, their desires, their vibrations are constantly influencing your own. The physicist Christian Huygens, in the 17th century, discovered the phenomenon of entrainment, the tendency of coupled oscillators to synchronize their rhythms. He observed that two pendulum clocks, mounted on the same wall, would, over time, begin to swing in perfect synchrony. Our consciousness may behave in a similar way. We are constantly being entrained by the vibrational fields of the people and the culture around us. We are part of a collective, consensual dream. Psychoactive substances can create the temporary illusion of breaking free from this consensual reality, of charting a new, ecstatic path high above the baseline. But this is often a false freedom. The crash that follows can leave us even more deeply enmeshed in the negative, downward pull of our own and the collective shadow. True freedom is not about escaping the system, but about becoming a more conscious and intentional participant within it. It is about learning to navigate the complex currents of the collective field with wisdom, with compassion, and with a clear sense of our own unique purpose. It is about understanding that while we cannot control the entire ocean, we can learn to become skillful sailors of our own small vessel. This brings us to the deep and often difficult question of personal accountability. In a universe of such vast complexity and interconnectedness, it can be easy to feel like a victim of external forces, to blame our circumstances on bad luck, on an unjust society, or on the ill intentions of others. And there is no doubt that these external factors are real and powerful. But the dimensional viewpoint also reminds us that at every moment, we are making choices, we are collapsing possibilities, we are co-creating our own reality. To take responsibility for our lives is not to deny the existence of external constraints, but to focus on our own unique sphere of influence, to become more conscious of the choices we are making, the stories we are telling ourselves, and the vibrational energy we are putting out into the world. It is to recognize that even a single, small, and conscious choice can send ripples of change throughout the entire interconnected system. But even as we embrace our own creative power, we must also embrace our limitations. Our human consciousness, as extraordinary as it is still just one finite perspective within an infinite, multidimensional reality. The higher dimensions of existence, the realms of other universes, of other physical laws, of realities that are beyond our current capacity to even imagine, these will likely always remain beyond our direct control or even our comprehension. We are both powerful creators and humble participants, masters of our own small corner of the cosmos, and children in a much grander and ultimately mysterious universal home. The illusion of control, then, is a double-edged sword. To believe that we have no control is to succumb to a state of helpless victimhood. To believe that we have total control is to fall into the trap of arrogant delusion. The path of wisdom lies in the middle, in the graceful dance between agency and surrender, between shaping our reality and being shaped by it. It is the recognition that we are both the artists and the clay, the dreamers and the dream, the individual notes and the grand cosmic symphony. And it is in the holding of this beautiful, paradoxical, and life-giving tension that we can find our true power, our true freedom, and our true place in the vast, interconnected, and endlessly creative unfolding of the cosmos. The 10th dimension. In the conceptual hierarchy we have been exploring, represents the ultimate, all-encompassing reality, the point of origin and the final container for all of existence. It is a concept that is so vast, so total, that it pushes our language and our imagination to their absolute limits. It is the realm where all possibilities, all timelines, all universes, all physical laws are not just potential, but are, in some deep and mysterious sense, actual. To visualize this, let us return to our analogy of the dimensional camera. A first-dimensional camera would just capture a single point. A second-dimensional camera could capture a line. A third-dimensional camera, like our own, captures a flat, two-dimensional image of a three-dimensional world. A fourth-dimensional camera would capture an entire world line, the complete history of an object from its birth to its death, all at once. A fifth-dimensional camera would capture the entire branching tree of all possible histories for a particular object. A sixth-dimensional camera could capture the entire phase space of all possible histories of our entire universe, given its specific initial conditions and physical laws. A seventh, eighth, and ninth-dimensional camera would capture the vast cosmic library of all possible universes, with all their different laws and initial conditions. The 10th dimensional camera, then, would be the ultimate, final snapshot. It would be a single, dimensionless point that contains, within it, all of these other dimensions, all of these other possibilities, all at once. It is the point of infinite density, not of matter, but of information. It is the everythingness from which the somethingness of our experienced reality emerges. This is a concept that has deep resonances with the ideas of many of the world's mystical and philosophical traditions. The Brahman of the Vedanta, the Ein Sof of the Kabbalah, the Tao of Taoism, these are all attempts to name the unnameable, to describe the ultimate, undifferentiated, and all-encompassing ground of being from which all manifest reality arises. The 10th dimension, in this conceptual sense, is not a place we can travel to. It is the source we have come from. And it is a source that is, in principle, beyond our ability to fully comprehend. The Austrian logician Kurt Gödel, in his famous incompleteness theorems, showed that any formal mathematical system that is complex enough to contain basic arithmetic will always contain true statements that cannot be proven. Within that system, to prove them, you need to step outside the system and use a larger, more comprehensive set of axioms. But this new, larger system will have its own new set of unprovable truths, and so on. In an infinite regress, Gödel's theorems are a profound statement about the inherent limitations of formal systems. And if our universe is, as some have suggested, a mathematical structure, then Gödel's theorems imply that it can never contain a complete and consistent description of itself. There will always be aspects of reality that are true but are unprovable from within the system. The 10th dimension, in this light, can be seen as the ultimate meta-system, the all-encompassing reality that contains all the other limited systems, but which cannot itself be fully described or understood from within any of them. It is the ultimate context, the final undrawable frame of the cosmic picture. The theory of superstrings provides a more physical, if no less abstract, picture of this ultimate reality. In this theory, all the particles and forces of our universe are the result of the different vibrational modes of tiny, one-dimensional strings. And these strings are thought to be vibrating in a 10-dimensional spacetime. The specific way in which the extra 6 dimensions are curled up, the geometry of the Calabi-Yau manifold, is what determines the specific spectrum of vibrations, and therefore, the specific set of physical laws and particles of our particular universe. The 10th dimension, in this picture, is the fundamental, underlying reality in which the cosmic symphony of the strings is played. The different universes of the multiverse correspond to different possible geometries, different possible symphonies. Our universe is just one particular piece of music, one particular solution to the fundamental equations of string theory. The concept of the 10th dimension also sheds a new light on the seemingly intractable paradoxes of our own experience, like the paradox of Zeno, which argues that motion is impossible because to get from point A to point B, you must first cross half the distance, and then half of the remaining distance, and so on, in an infinite series of steps. In a classical, continuous spacetime, this is a real logical puzzle. But in a universe where space and time may be quantized at the Planck scale, where there is a smallest possible unit of distance and a smallest possible unit of time, the paradox dissolves. The infinite regress is halted by the fundamental, discrete nature of reality itself. In a similar way, the 10th dimension, as the ultimate foundational reality, can be seen as the ultimate quantifier, the point that halts the infinite regress of why questions. Why are the laws of physics the way they are? Because they are the result of the specific geometry of the extra dimensions. Why this geometry? Because it is one of the many possible solutions to the equations of string theory. Why string theory? Why 10 dimensions? At some point, the chain of explanation must end, not in an arbitrary fact, but in a final, all-encompassing, and self-consistent structure. The 10th dimension, in this conceptual framework, is that final structure. It is the ultimate, it is what it is. This is not a dismissal of the question, but a recognition of the limits of explanation. It is an invitation to a state of profound, intellectual and spiritual awe, a state of learned ignorance in the face of a reality whose ultimate nature is so vast, so complete, and so all-encompassing that it can only be pointed to, hinted at, and wondered about. It is the silent, dimensionless, and infinitely pregnant point from which all the beauty, all the complexity, and all the wonder of our multidimensional cosmos is born. The intricate tapestry of reality, as woven by the threads of quantum mechanics and higher dimensions, is a reality of profound interconnectedness. The different dimensions are not separate, isolated realms. They are layers of a single, unified structure, constantly interacting and influencing each other. And our own experience, our own consciousness, is not a separate, detached entity. It is a point of intersection, a place where these different layers of reality meet, overlap, and create the rich, multifaceted world we inhabit. To understand this, let us consider the interplay between what we can call physical systems and memic systems. A physical system is the world of our three-dimensional bodies, of matter and energy, of the deterministic cause and effect laws of classical physics. A memic system, a term coined by the biologist Richard Dawkins, is the world of ideas, of beliefs, of cultures, of stories. It is the abstract, informational realm of the mind. These two systems are not separate. They are in a constant dynamic feedback loop. Our physical reality shapes our thoughts and beliefs, and our thoughts and beliefs, in turn, shape our physical reality. A new scientific theory, a meme, can lead to the development of a new technology that fundamentally alters our physical world. A powerful religious or political ideology can shape the course of history, leading to the rise and fall of empires. This interplay between the physical and the memic can be visualized in our dimensional framework. Our physical lives unfold along a specific four-dimensional timeline, a particular path through the fifth-dimensional possibility space. But our memic lives, the lives of our ideas and beliefs, are not so constrained. An idea can travel across time and space. It can connect different cultures. It can influence the choices that lead to the branching of different timelines. The memic system exists, in a sense, at a higher dimensional level, a level that can create interference patterns between the different potential realities of the physical world. A powerful shared belief, a dominant meme, can act as a kind of observer, collapsing the wave function of a collective reality, steering the course of a society or a civilization along a particular path. A cultural revolution, a scientific paradigm shift, a spiritual awakening. These are all moments where a new memic pattern creates a powerful interference effect, fundamentally altering the shape of our shared physical timeline. This concept of interference and overlap is not just a metaphor. It is a deep feature of the quantum world. The interference pattern in the double-slit experiment is a direct result of the overlap of the two possible paths of the electron's wave function. And in the higher dimensional reality of string theory, the properties of our universe are determined by the complex interference patterns of the vibrating strings as they move through the multidimensional Calabi-Yau space. Our experienced reality is an interference pattern, a product of the overlap and interaction of a vast number of underlying potential realities. We, as conscious beings, are the points at which this interference becomes manifest. We are both the product of our physical, four-dimensional reality, and the conduits for the higher dimensional, memic systems that flow through us. We are living at the intersection of worlds. This perspective gives us a new and powerful way to understand the tension between determinism and free will. Our physical bodies are subject to the deterministic laws of physics. Our lives are constrained by the circumstances of our birth, by the society we live in, by the history that has preceded us. This is the particle aspect of our being, but our minds, our consciousness, have access to the wave aspect, to the higher dimensional realm of possibility, of imagination, of choice. We have the freedom to introduce new ideas, new memes, into the system, to create new interference patterns, to choose which possibilities to collapse into our shared reality. Our free will is not the freedom to violate the laws of physics, but the freedom to navigate the possibility space that those laws allow. It is the freedom to choose which story to tell, which dream to follow, which future to create. The universe, in this view, is a vast information processing system, a cosmic computer that is constantly exploring its own infinite computational potential. And we, as conscious mimic beings, are the universe's own agents of exploration, its own way of introducing novelty, of creating new patterns, of pushing the boundaries of what is possible. This brings us to a final, profound, and deeply humbling realization: the journey to understand the universe, from the smallest quantum flicker to the vastest cosmological structures, is not just a journey out there. It is also a journey in here. The same principles of superposition, of uncertainty, of entanglement, of dimensional overlap that govern the cosmos are also at play in the deep, mysterious, and endlessly creative landscape of our own consciousness. The structure of the universe and the structure of the mind are not two separate things. They are reflections of each other, two different expressions of the same, underlying, informational reality. The cosmic web of galaxies and filaments is mirrored in the neural web of our own brains. The branching timelines of the multiverse are mirrored in the branching possibilities of our own choices. The creative power of the quantum vacuum is mirrored in the generative silence of our own deep, contemplative states. To study the universe is to study ourselves, and to study ourselves is to study the universe. We are not just in the cosmos is in us. This is the ultimate, non-dual truth that lies at the heart of both the most ancient spiritual wisdom and the most advanced modern science. It is a truth that can be intellectually understood, but can only be truly known through direct, subjective experience. And the most universal and accessible portal to this experience is the nightly, sacred, and deeply mysterious journey of sleep. In sleep, we let go of our attachment to the collapsed, classical world of our waking identity, and we dissolve back into the quantum, superpositional, and multidimensional sea of pure potential. We become the universe, dreaming itself. We are the interference pattern between the seen and the unseen, the known and the unknown, the finite and the infinite. And in this beautiful, paradoxical, and life-giving dance, we find our true home, our true nature, and our true place in the grand, magnificent, and endlessly unfolding story of the cosmos. The concept of a 10-dimensional reality, while a cornerstone of advanced theoretical physics like string theory, remains one of the most challenging ideas for the human mind to grasp. Our entire evolutionary history has conditioned us to perceive and navigate a world of 3 spatial dimensions and 1 of linear time. To venture beyond this familiar framework requires a leap of imagination, a willingness to embrace abstraction, and a deep appreciation for the power of mathematics to describe realities that lie beyond the reach of our senses. The journey to the 10th dimension is a journey of conceptual scaffolding, building layer by layer, from the simple and intuitive to the complex and counterintuitive. We begin with the 0th dimension, a single, dimensionless point. It has no size, no extension, it is pure location. This is the ultimate abstraction, the conceptual seed from which all of geometry grows. From this point, we can extrude a line, creating the first dimension, the world of pure length. A being in this one-dimensional world could only move forward or backward along this line. The second dimension is created by adding a new direction, perpendicular to the first, creating a plane, a world of length and width. This is the world of flatland. The famous thought experiment proposed by the 19th century schoolmaster Edwin Abbott, the inhabitants of flatland. Two-dimensional shapes like squares and triangles can move left and right, forward and backward, but they have no concept of up or down. A three-dimensional object, like a sphere, passing through their two-dimensional world would appear as a mysterious and magical event, a point that grows into a circle, and then shrinks back to a point before disappearing completely. For the Flatlanders, the third dimension is a realm of incomprehensible, godlike power. And this is a powerful analogy for our own relationship with the higher dimensions. We are the inhabitants of a three-dimensional spaceland. By adding a third direction, depth, we gain the world of solid objects, of volume, of the rich, physical reality we experience every day. But what if our three-dimensional world is just a slice, a cross-section, of a higher dimensional reality? The fourth dimension, in the most common physical interpretation, is time, but it is not the flowing, transient time of our subjective experience. It is a spatialized time, a dimension along which the entire history of the three-dimensional universe is laid out. A four-dimensional being could perceive our entire lifespan, from birth to death, as a single, static, four-dimensional object, a space-time worm. They could see all the moments of our lives at once, just as we can see all the points on a line at once. This block universe view is a direct consequence of Einstein's theory of relativity, and it is a profoundly deterministic picture of reality. But the story does not end there. The fifth dimension, in the conceptual framework we are building, introduces the idea of possibility, of alternate realities. If every quantum event, every choice, causes the universe to split, then the fifth dimension is the space that contains all these branching, parallel timelines. A fifth-dimensional being could not only see our entire history, but could also see all the other possible histories that could have unfolded from the same starting point. They could see the you who took the other job, who married the other person, who made the other choice. The fifth dimension is the landscape of the might-have-beens. The sixth dimension takes this a step further. It is the plane that contains all of these possible histories, all of these branching timelines that arose from the specific initial conditions of our Big Bang. And it allows for a folding of this possibility space, a shortcut between different, seemingly distant branches. It is the complete phase space of our particular kind of universe. The seventh dimension marks a profound leap into an even greater level of abstraction. It is the dimension that contains the set of all possible universes that could have started with different initial conditions and different physical laws. This is the realm of the Level 2 multiverse of eternal inflation, a library of all possible cosmic beginnings. In one universe, gravity might be a repulsive force. In another, there might be 4 spatial dimensions. In a third, the speed of light might be different. The seventh dimension is the space that contains all these different and mutually inaccessible cosmic rulebooks. The eighth dimension is the plane that contains all of these different seventh-dimensional libraries, allowing for a branching, a comparison between these fundamentally different kinds of realities. The ninth dimension is the ultimate ensemble, the dimension that contains all possible physical laws, all possible initial conditions, all possible histories, all at once. It is the set of all possible universes, the complete catalog of all that is physically possible. And this brings us, finally, to the 10th dimension. In this hierarchical, conceptual model, the 10th dimension is the ultimate point of origin, the dimensionless, abstract point that contains, within it, all of the other, lower dimensions, and all of the infinite possibilities they represent. It is the point of everythingness, the ultimate ground of being from which all manifest reality, in all its infinite variety, unfolds. It is a concept that is almost pure metaphysics, a point where the language of physics and mathematics touches the language of mysticism and philosophy. But it is a concept that has a more concrete, if no less abstract, home in the framework of superstring theory. The mathematical consistency of superstring theory, the leading candidate for a theory of everything, requires a 10-dimensional spacetime. In this theory, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. And the different ways these strings can vibrate, the different notes they can play, are what give rise to the different particles and forces we see in our universe. The properties of these vibrations are determined by the geometry of the 6 extra compactified dimensions. So, the 10th dimension, in this more physical picture, is the fundamental, underlying arena in which the cosmic symphony of the strings is played. The landscape of the 10 to the power of 500 possible vacuum states of string theory corresponds to the vast multidimensional possibility space we have been exploring. Each possible way of curling up the extra dimensions corresponds to a different possible universe, a different set of physical laws, a different symphony. Our universe is just one particular, beautiful, and life-bearing piece of music, played on the 10-dimensional instrument of the cosmos. This journey through the dimensions is a powerful exercise in expanding our own conceptual horizons. It is a journey that takes us from the familiar and the concrete to the abstract and the unimaginable. It is a journey that should instill in us a profound sense of humility, a recognition of the severe limitations of our own three-dimensional perception. And it is a journey that should also fill us with a sense of wonder. A wonder at the possibility that the reality we experience is just a thin, fragile, and beautiful membrane, a single slice of a much grander, much richer, and much more mysterious, multidimensional cosmos. The 10th dimension, whether as a conceptual endpoint or a physical reality, is a powerful symbol of the infinite, creative potential that lies at the heart of existence, a potential that is both the source of our universe and the source of our own. Endless capacity to imagine, to question, and to explore. The participatory nature of reality, as suggested by the strange and beautiful world of quantum mechanics, is one of the most profound and revolutionary ideas in the history of human thought. It is an idea that challenges our most basic common sense assumptions about the world. And it is an idea that is still, a century after its birth, the subject of intense debate and a source of deep philosophical unease for many. The classical, Newtonian worldview, which has shaped our thinking for 300 years, is a worldview of a clockwork universe, a universe of solid, definite objects moving in a fixed, absolute space and time, governed by deterministic laws. It is a universe that exists out there, independent of our own minds, a universe that we can, in principle, observe and understand without affecting it. Quantum mechanics shatters this picture. It tells us that at the fundamental level, reality is not a collection of definite things, but a web of interconnected probabilities. A particle does not have a definite position or a definite momentum until it is measured. It exists in a superposition of all possible states, a wave function that describes the probability of finding it here or there, or with this momentum, or that one, and it is the very act of measurement, of observation, that seems to be the mysterious ingredient that collapses this wave of probability into a single, definite reality. This is the observer effect, the strange and unsettling fact that the world we see seems to be, in some deep and fundamental way, shaped by the very act of our seeing it. This has led to a host of perplexing questions and a zoo of different interpretations. Does this mean that we are literally creating reality with our minds? The answer for most physicists is a qualified no. The observer effect is not about a mystical power of consciousness to will things into being. It is a consequence of the fact that any act of measurement, any interaction with a quantum system, is a physical process that necessarily disturbs that system. To measure an electron, you have to bounce a photon off of it, and this interaction inevitably changes its state. In this view, the observer does not need to be a conscious being. A simple, inanimate particle detector is enough to cause the wave function to collapse, but this just pushes the mystery back a step. What is it about the interaction with a macroscopic, classical measuring device that is so special? Why does it have the power to collapse the quantum superposition? This is the heart of the measurement problem, and it is a problem that has not been definitively solved. The decoherence program has provided a partial answer, showing how a quantum system rapidly loses its superpositional nature as it becomes entangled with the vast number of degrees of freedom in its environment. But decoherence does not explain which specific outcome is chosen from the initial superposition. It just explains why we do not see macroscopic superpositions. The many worlds interpretation offers a radical and elegant way out of this puzzle. It simply denies that the collapse ever happens. The wave function is the complete and total description of reality, and it always evolves in a smooth, deterministic way according to the Schrödinger equation. When a measurement is made, the universe does not collapse into a single state. It branches. The observer becomes entangled with the system, and the entire world splits into multiple parallel realities, one for each possible outcome. In one branch, the electron is found at position A. In another, it is found at position B. There is a version of you that experiences each outcome. In this view, we are not collapsing reality. We are simply experiencing one particular branch of a vast and constantly splitting quantum multiverse. This is a breathtakingly grand and logically consistent picture, but it comes at the price of accepting an almost unimaginable ontological extravagance and infinite number of parallel, unobservable worlds. But regardless of which interpretation one prefers, the central, participatory nature of the quantum world remains. We are not detached spectators of a pre-existing reality. We are entangled participants in a cosmic drama, a drama where the questions we ask, the measurements we make, the choices we take, all play a crucial role in shaping the reality that unfolds. This has a powerful and direct parallel in our own subjective lives. The reality we experience is not a passive reception of external data. It is an active, co-creative process. Our beliefs, our expectations, our attention, all act as a kind of filter, collapsing the infinite, superpositional potential of the world into a single, experienced reality. If we believe the world is a hostile and dangerous place, we will tend to notice and amplify the evidence that confirms this belief. If we believe the world is a place of beauty and opportunity, we will tend to experience a reality that reflects this. Our consciousness is not just a mirror reflecting the world. It is also a lamp that illuminates it, and in illuminating it helps to bring it into being. This does not mean that we have absolute, solipsistic control over reality. We are still bound by the underlying probabilistic laws of the wave function, both in the physical world and in our own psyches. But we do have a choice. We have the choice of where to direct our attention, which questions to ask, which possibilities to engage with. And this choice is a creative, world-shaping act. This is the deep and beautiful truth that the participatory universe reveals to us. It is a truth that calls us to a new level of responsibility, a new level of conscious participation in the ongoing creation of our own lives and of our shared world. And it is a truth that can be most profoundly felt in the quiet, creative, and dreamlike spaces of our own inner world, A world where we are, at every moment, both the artist and the canvas, the observer and the observed, in the grand, magnificent, and endlessly unfolding masterpiece of reality.